Look up at the night sky, and what do you see? A vast, silent expanse dotted with stars, each one seeming solitary and unchanging. But the truth is far stranger. Many of those stars aren't alone at all. In fact, nearly half the stars in our galaxy are locked in a dance with a partner, whirling around each other in systems so bizarre, they defy everything we thought we knew about the cosmos. Welcome to the wild, unpredictable world of binary star systems where two stars share an orbit, creating phenomena so extraordinary they seem ripped straight from science fiction. Imagine a place where twin stars circle so close they nearly touch, their gravity stretching them into teardrop shapes, or where one star steals matter from the other until it erupts in a cataclysmic explosion. Picture a system where the two stars couldn't be more different, one a blazing giant, the other a dense corpse, locked together in a cosmic tug of war. These aren't just rare oddities, they're laboratories for the universe's most extreme physics, revealing secrets about gravity, time, and even the origins of life itself. Today, we're diving into 50 of the strangest discoveries ever made about binary star systems, each one more mind-bending than the last. From stars that warp space-time like a funhouse mirror to pairs that blast out deadly radiation across the galaxy, these cosmic duos challenge our understanding of reality. Why do some binary stars explode in violent supernova while others fade quietly into darkness? How can these systems create conditions so extreme they shouldn't even exist? Strap in, because by the end of this journey, you'll never look at the night sky the same way again. The universe is stranger, fiercer, and more beautiful than we ever imagined. And it all starts with two stars bound together by forces beyond our wildest dreams. One of the most bizarre behaviors in the cosmos happens when a star turns into a cosmic vampire, slowly draining the life from its companion over millions of years. Picture two stars locked in a tight orbit where one star grows larger and hungrier, reaching out with its gravity to steal gas straight from the surface of its partner. This isn't science fiction, it's a real phenomenon called mass transfer, and it creates some of the most violent and unpredictable systems in the universe. The vampire star, often a dense white dwarf or neutron star, doesn't just siphon material evenly, it rips it away in chaotic streams, forming a swirling disk of superheated plasma around itself. As this stolen matter crashes onto the surface of the vampire, it can trigger colossal thermonuclear explosions called nova, lighting up the galaxy in bursts of light visible across millions of light years. In extreme cases, the buildup of stolen material can even push the vampire star past a critical limit, causing it to detonate in a cataclysmic supernova, obliterating both stars in an instant. But the victim star isn't helpless, it fights back. The transfer of mass alters the balance of gravity between the two, leading to wild orbital shifts. Sometimes the stolen gas forms unstable bridges between the stars, creating whip-like tendrils of superheated matter lashing through space. Other times, the donor star retaliates by erupting in violent flares, blasting away material before the vampire can claim it. This cosmic tug-of-war leaves both stars dramatically changed, one bloated and rejuvenated by fresh fuel, the other stripped down to its core, destined to fade away. Astronomers study these vampiric pairs to understand how matter behaves under extreme gravity, and the discoveries keep getting weirder. Some vampire stars don't just siphon gas, they warp space-time around them, spinning so fast they distort the fabric of reality. Others create bizarre hybrid stars where the stolen material forms exotic layers of elements that shouldn't exist under normal conditions. These systems are more than just celestial oddities. They're natural laboratories showing us how stars evolve, explode, and sometimes how they die in spectacular fashion. If you think vampire stars are extreme, wait until you meet the Black Widow, a celestial predator so lethal it doesn't just consume its companion, it vaporizes it. This cosmic horror shows stars a pulsar, the super-dense corpse of a dead star spinning hundreds of times per second, blasting its partner with radiation so intense it's literally cooking the star alive. The Black Widow pulsar earned its name for a gruesome reason. Like its eight-legged namesake, it's in the process of destroying its mate. Locked in a tight orbit, the pulsar's beams of high-energy radiation, twin death rays shooting from its magnetic poles, sweep across its companion star like a cosmic blowtorch. Over millions of years, this relentless assault heats the star's surface to unimaginable temperatures, stripping away layers of gas and flinging them into space. Astronomers call this ablation, a clinical term for a brutal process where the victim star loses mass faster than it can hold itself together. But here's where it gets even stranger. The pulsar isn't just melting its partner, it's warping the very fabric of their relationship. As the companion star loses mass, their orbits tighten, forcing the doomed star into an ever faster death spiral. Some Black Widow systems whirl around each other in just hours, their orbits shrinking so rapidly that astronomers can measure the change over mere decades. In a final, macabre twist, the pulsar's radiation pressure may eventually blow away the entire outer layers of its companion, leaving behind nothing but a scorched core, a planetary mass ember adrift in space. What makes these systems so fascinating isn't just their brutality. It's what they reveal about the limits of stellar survival. The companion stars in Black Widow systems aren't small. Some are sun-like in size, yet they're being dismantled by forces no star should endure. Their suffering gives scientists a front-row seat to physics that defies intuition, where radiation alone can overpower gravity. And because pulsars are nature's most precise clocks, their spins so regular they rival atomic clocks. Watching their orbits decay helps test Einstein's theory of relativity with unmatched precision. Yet the Black Widow story might not end with a whimper. Some astronomers speculate that if the companion star holds on long enough, the pulsar's radiation could ignite nuclear reactions in its remaining gas, creating sporadic bursts of light like cosmic distress signals. Others believe these systems might eventually collapse into exotic binaries, where the pulsar orbits the ghostly remnant of its victim, a silent testament to one of the universe's most one-sided duels. Whether you see them as cosmic tragedies or extreme physics experiments, Black Widow pulsars remind us that the universe doesn't play fair. In the endless dance of binary stars, sometimes one partner leads and the other doesn't just follow. It burns. Science fiction got it right. Binary star systems with twin suns aren't just the stuff of Star Wars fantasy. In a twist worthy of Hollywood, astronomers have found real-life versions of Tatooine, where planets orbit two stars instead of one, witnessing double sunrises, dramatic eclipses, and skies lit by a pair of blazing orbs. But unlike Luke Skywalker's home planet, the reality of these worlds is far more chaotic and far more fascinating. Take Kepler 16b, the first confirmed planet discovered orbiting two stars. This gas giant, about 200 light-years away, doesn't just enjoy scenic twin sunsets, it survives in a gravitational roller coaster. The stars it orbits are a mismatched pair, one a small, dim red dwarf, the other an even smaller, cooler star. Their dance is so tight they complete an orbit in just 41 days, while the planet loops around them both in a wide, wobbling path. The result: wild temperature swings, erratic seasons, and a sky where the suns constantly chase each other, sometimes eclipsing one another in a celestial game of hide and seek. But the real surprise is how common these systems might be. Scientists estimate that half of all sun-like stars have companions, meaning planets with double suns could outnumber solitary ones in the galaxy. Some of these worlds orbit so-called wide binaries, where the stars are far apart, creating stable but bizarre conditions like a planet that spends decades in twilight under one sun before migrating into the searing glare of its twin. Others circle close binaries, where the stars whirl around each other so fast their gravity yanks any nearby planets into stretched, oval-shaped orbits. These worlds endure brutal tidal forces, with surfaces likely torn by constant quakes and volcanic eruptions. The most extreme cases defy imagination. In the system HD 1360-34, two massive stars orbit each other every 16 days, surrounded by a swirling disk of dust where planets might form. But here's the catch: the larger star is a volatile B-type star, spinning so fast it flings off its own equator, creating a rotating death trap of superheated gas. Any planet forming here would grow up in a hurricane of stellar material, bombarded by shockwaves and bathed in lethal radiation. Yet despite the chaos, life might still find a way. Some double-star systems have habitable zones, regions where temperatures could allow liquid water, though the definition of habitable gets stretched to its limits. On a planet orbiting two dim red dwarfs, for example, the combined warmth might create a narrow band where life could cling to existence, though the skies would glow an eerie red, and solar flares from both stars could regularly blast the surface with deadly radiation. What makes these systems so valuable to scientists isn't just their cinematic appeal, it's the way they challenge our ideas about how planets form. In a single star system like ours, planets coalesce from an orderly disk of gas and dust. But around binary stars, gravity carves the disk into twisted, asymmetric shapes, forcing planets to assemble in a cosmic construction zone where the rules keep changing. Some worlds might get kicked out entirely, sent drifting into interstellar space as rogue planets. Others could end up with bizarre, tilted orbits, looping over the poles of their twin suns instead of circling neatly around their equators. The discovery of these real-life Tatooines has reshaped the search for extraterrestrial life. If planets can survive, even thrive, in such turbulent environments, the galaxy's menu of potential habitats just got a lot bigger. Maybe life out there isn't limited to calm, Earth-like worlds. Maybe it's clinging to a storm-racked planet under twin suns where the sky tells two stories at once, and every sunset is a reminder that the universe loves a good drama. In the quietest corners of the universe, some binary stars don't just die, they become ghosts, locked in a slow-motion waltz toward oblivion. These are the systems where both stars have burned out, collapsing into white dwarfs, the dense, Earth-sized cores of dead suns. But their story doesn't end there. Without the energy of nuclear fusion to hold them up, these stellar corpses are governed solely by gravity, spinning closer and closer together in a dance that can last billions of years. Until it ends in one of the most violent explosions known to science. What makes these pairs so eerie isn't just their fate, it's the music they create along the way. As they orbit, their immense gravity ripples the fabric of space-time itself, sending out waves that travel across the cosmos at the speed of light. These gravitational waves, first predicted by Einstein, are so faint that detecting them required some of the most sensitive instruments ever built. Yet when scientists finally tuned in, they heard something extraordinary. The universe's background hum, filled with the whispers of countless dead stars spiraling toward their doom. But the finale is where things get truly spectacular. As the white dwarfs lose energy, their orbits decay, drawing them inexorably closer. If the pair is lightweight enough, they might merge quietly, forming a single, more massive white dwarf. But if their combined mass crosses a critical threshold about 1.4 times the mass of our Sun, the merger triggers a runaway thermonuclear explosion. In seconds, the carbon and oxygen packed inside them detonates like a cosmic bomb, obliterating both stars in a Type 1, a supernova. These blasts are so uniform in brightness, astronomers use them as standard candles to measure distances across the universe. Yet the most baffling part, some of these doomed duos shouldn't exist at all. Theory suggests that if two white dwarfs get too close, one should shatter under tidal forces long before they collide. But nature, as always, defies expectations. Systems like J0806.4153, two white dwarfs orbiting each other in a dizzying 51 minutes, challenge everything we thought we knew. How did they survive so long without tearing each other apart? What secrets do they hold about the final moments before a supernova? The answers might rewrite our understanding of stellar death. Some models suggest these mergers don't always result in explosions instead. They could collapse directly into neutron stars or even black holes without a visible supernova at all. Others propose that merged white dwarfs might reignite briefly, becoming bizarre, zombie stars that glow with stolen nuclear life. One thing's certain, when these dancing dead stars finally meet, they don't go quietly. They paint the cosmos with the ashes of their destruction, spewing out elements like iron, silicon, and calcium, the very building blocks of planets and life. In a way, we're all made from the echoes of these ghostly duets, the last waltz of stars that refuse to fade away without a final, earth-shattering encore. At the heart of the Cygnus constellation, astronomers stumbled upon a cosmic paradox, a binary system so baffling it rewrites the rules of stellar life and death. The larger star, a blue supergiant, burns with the intensity of 2 million suns. Its companion, a neutron star so dense, a teaspoon of its material would weigh 1 billion tons on Earth. Normally, such a pairing would make sense. Massive stars often leave behind neutron stars when they explode. But here's the catch: the blue supergiant shouldn't be here at all. According to every model of stellar evolution, it should have died billions of years ago. This cosmic oddball, known as LB1, defies logic. The blue supergiant is 80 times more massive than our Sun, a behemoth that should have burned through its fuel in just a few million years before collapsing into a black hole. Yet somehow, it's still shining brightly, orbiting its neutron star partner as if mocking the laws of physics. Theories abound. Maybe the neutron star's gravity somehow siphoned off just enough material to keep the supergiant alive, like a stellar life support system. Or perhaps the system underwent a near-fatal encounter with a third star, a cosmic collision that reshaped their fates, but the most tantalizing possibility. This neutron star wasn't born from a supernova at all. Some researchers suggest the original star might have collapsed directly into a neutron star without exploding, a phenomenon called a failed supernova. In this scenario, the star's core imploded so efficiently that the outer layers fell inward instead of being blasted into space, leaving the companion star untouched. If true, it would explain why the blue supergiant survived, but it would also mean we've been wrong about how massive stars die. What makes LB1 truly extraordinary isn't just its existence, it's the implications. If stars can collapse silently without the fanfare of a supernova, how many other cosmic ghosts are lurking undetected? And if binary systems can cheat stellar death, what other illusions hide in plain sight? For now, LB1 remains an enigma, a blazing rebel in a universe that supposedly plays by strict rules, whispering secrets we're only beginning to decode. Some stars don't just drift through the galaxy, they're launched into the void like cosmic cannonballs, hurtling through space fast enough to escape the Milky Way entirely. These hypervelocity stars, some racing at over 1 million miles per hour, weren't born this way. They're runaways flung into the abyss by the gravitational chaos of binary systems gone wrong. The drama starts when a binary pair wanders too close to the supermassive black hole at the galaxy's heart. As the black hole's immense gravity pulls the two stars apart, one gets captured into a tight orbit, while the other is slingshotted outward at mind-blowing speed, like a stone from a sling. In less than a second, the ejected star goes from a peaceful orbit to an interstellar fugitive, streaking across the galaxy with enough velocity to leave it behind forever. But black holes aren't the only culprits. Sometimes the explosion of one star in a binary system can send its companion careening away. When a supernova detonates, the sudden loss of mass releases the surviving star from gravity's grip like cutting a tether. The shockwave delivers an extra kick, propelling the star forward like a surfboard catching a tidal wave. The result, a rogue star glowing and alone, destined to drift between galaxies with no place to call home. These stellar outcasts aren't just curiosities, they're cosmic breadcrumbs, revealing secrets about the environments that launched them. By tracing their paths backward, astronomers can map the invisible forces that shaped their journeys from the Milky Way's central black hole to long-dead supernova. Some hypervelocity stars even carry traces of their lost companions in their chemical makeup, like scars from a violent breakup written in starlight. The fastest known runaway, a star dubbed S5HVS1, is rocketing through space at over 4 million miles per hour, so fast it's already left the galaxy's outskirts and entered the uncharted wilderness of intergalactic space. But here's the twist, not all runaways are fleeing. Some are actually chasing like the blue stragglers, stars that steal fuel from companions to appear younger and brighter, only to be ejected later, burning hotter and living longer than their peers. Whether flung by black holes, blasted by supernova, or shoved aside in stellar collisions, these rogue stars remind us that the universe is anything but orderly. Gravity giveth, and gravity taketh away, sometimes with enough force to send a star flying into the endless dark, a solitary traveler on a journey without end. Astronomers have witnessed stars vanish before swallowed by black holes, obliterated in supernova, or dimmed to obscurity. But in the late 1600s, they documented something even stranger, a star that disappeared from the night sky, only to return centuries later like a cosmic ghost. This is the tale of T Coronii Borealis, a binary system with a flair for the dramatic, where one star plays a vanishing act so precise it defies belief. At first glance, T Coronii Borealis, or TCRB for short, looks unremarkable, a faint speck in the constellation Corona Borealis, the Northern Crown. But in 1866, it erupted without warning, blazing brighter than 1,000 suns for a week before fading back into obscurity. Then, in 1946, it did it again, flaring to naked eye visibility before vanishing once more. The culprit, a white dwarf locked in a deadly embrace with a red giant, siphoning hydrogen from its swollen companion until the stolen gas reaches critical mass, triggering a runaway thermonuclear explosion on its surface. These eruptions, called recurrent nova, should follow a predictable schedule, but TCRB had another trick up its sleeve. After its 1946 outburst, astronomers expected the star to remain quiet for another 80 years. Then, in 2015, something impossible happened. The system's red giant companion disappeared. Telescopes trained on the spot showed only the white dwarf glowing faintly against the void. Had the red giant collapsed, been devoured, theories swirled until, just as mysteriously, the star flickered back into view in 2021 as if it had never left. The truth is even wilder. The red giant hadn't vanished, it had dimmed so drastically that even Hubble missed it. A thick shroud of dust, likely ejected during a hidden eruption, had wrapped around the star like a cosmic veil. Over years, radiation pressure from the white dwarf slowly cleared the debris, revealing the red giant once more. But here's the twist, this wasn't the first time. Digging through ancient records, scientists found accounts of TCRB's outbursts dating back to 1217, and every time the star disappeared beforehand. What makes TCRB so extraordinary isn't just its vanishing act, it's the precision of its cycle. Like a celestial clock, it erupts roughly every 80 years, with its red giant dimming on schedule like a backstage cue. This reliability lets astronomers study the lead up to a nova in real time, watching for clues in the star's flickering light. Right now, TCRB is overdue for another eruption, and when it comes, it'll be the first nova humans have predicted in advance, a fiery encore to a performance centuries in the making. For astronomers, TCRB is more than a curiosity, it's a Rosetta Stone for understanding stellar resurrection. Most nova leave their donors intact, but recurrent ones like this slowly erode their companions over millennia. Will the red giant survive another cycle, or will the white dwarf's hunger finally consume it? Whatever happens, TCRB proves that in the cosmos, even death can be provisional, and sometimes the stars we mourn aren't gone. They're just waiting for their next cue. In a cosmic twist that redefines what it means to cheat death, astronomers have discovered a star that somehow survived its own funeral. Known as a zombie star, this bizarre object should have been obliterated in a supernova explosion, yet there it was, shining defiantly in the wreckage, as if it had clawed its way back from the grave. The secret to its resurrection, a binary companion that refused to let it die. The star, officially named LP40-145, was caught in a fateful dance with a smaller partner. When it reached the end of its life and detonated as a supernova, the explosion should have vaporized it entirely, leaving behind only a neutron star or black hole. Instead, observations revealed a surviving core, a white dwarf still glowing amid the debris, seemingly unscathed by the apocalypse around it, the only explanation. In its final moments, the dying star gorged on hydrogen stolen from its companion, using the fresh fuel to temper the blast and shield its core from total annihilation. This stellar Lazarus act isn't just rare, it challenges everything we know about supernova. Normally, a white dwarf can only survive if the explosion is a weaker, Type 1, a supernova, where the star burns from the inside out like an overfilled furnace. But LP40-145 was a Type 2 supernova, the kind triggered when a massive star collapses under its own weight. That it left a remnant at all is like finding a building still standing after a nuclear blast. Even stranger, the zombie star isn't just surviving, it's thriving. Spectroscopy shows it's still siphoning material from its companion, rebuilding itself from the scraps of its own destruction. The companion star, now stripped and scarred by the blast, orbits in a precarious embrace, its fate uncertain. Some theories suggest these revived stars might become hybrid chimeras, their cores fused with alien elements from the supernova's fallout, creating chemical compositions unlike anything else in the universe. But the most unsettling question remains: how many other supernovae have left zombie survivors hiding in plain sight? For centuries, astronomers assumed these explosions were total annihilations. Now, LP40-145 suggests that under the right conditions, with a binary partner to feed on, some stars might dodge death entirely. It's a cosmic loophole where the rules of stellar demise aren't just bent, they're rewritten. What happens next to this undead star is anyone's guess. Will it cannibalize its companion completely, growing stronger with every stolen bite? Or will its second life be cut short by another final collapse? For now, it remains a flickering enigma, a ghostly reminder that in the universe, even death isn't always the end sometimes. It's just the beginning of a far stranger story. There are cosmic predators, and then there's the star-swallowing black hole, a beast that doesn't kill its prey in one bite but feasts slowly, tearing chunks from its companion in a cycle of violence that lights up the galaxy. This is no ordinary black hole. It's part of a binary system called V404 Cygni, where every few decades the black hole awakens from its slumber, shredding its stellar partner in a spectacle of X-ray fury so bright it outshines entire galaxies. The horror unfolds like this: the companion star, a bloated giant, wanders too close to the black hole's event horizon. Gravity's grip stretches the star into a teardrop shape, peeling away layers of gas in a process called tidal disruption. But instead of swallowing the star whole, the black hole feeds in bursts. As stolen matter spirals inward, it forms a superheated disk around the black hole, glowing with temperatures exceeding millions of degrees. Friction within the disk builds until, like a pressure cooker exploding, it unleashes a colossal X-ray flare, visible across the cosmos. What makes this system so extraordinary isn't just the destruction, it's the precision. The black hole doesn't consume haphazardly. It dines in cycles, flaring every 20 to 30 years like clockwork. Astronomers liken it to a cosmic geyser, building pressure until it erupts in a jet of high-energy particles traveling at nearly the speed of light. These jets aren't steady, they flicker unpredictably, pulsing every few hours as if the black hole is chewing its meal in fits and starts. The companion star isn't just a passive victim, though. Each time the black hole feeds, the star fights back. Its gravity tugs on the stolen gas, creating whirlpools and eddies in the accretion disk. Sometimes the star's resistance flings matter clear of the black hole entirely, sending it careening into space like a splash from a monstrous tidal wave. Other times, the star's outer layers puff up in protest, briefly shielding itself from further damage, a temporary reprieve before the next feeding frenzy begins. These violent interactions are more than just a light show. They're a rare window into how black holes grow. Most supermassive black holes feed so slowly, their meals are invisible to us. But V404 Cygni's periodic feast let scientists study the process in real time, watching how gas spirals inward, how jets form, and how energy escapes the pull of an event horizon. Even stranger, this black hole is picky. Observations suggest it doesn't devour everything it tears away. Some gas gets too heated too quickly, escaping as high-speed winds before it can be swallowed. It's as if the black hole is a messy eater, scattering crumbs across the cosmic table. For the companion star, the future is grim. Each pass strips away more of its mass, dooming it to eventual annihilation. But for astronomers, every flare is a treasure trove, revealing secrets about gravity's extremes, and proving that even in the darkest corners of space, there's no such thing as a quiet meal. In the cosmic ballet of binary stars, gravity doesn't just pull, it sculpts. Imagine a star stretched like taffy, its spherical form warped into a teardrop or flattened into an egg, all because of the relentless tidal forces from its companion. This isn't science fiction, it's the reality for stars locked in tight orbits where gravity's grip is so fierce, it reshapes celestial bodies into bizarre, ever-changing forms. Take Beta Lyrae, a system where two massive stars orbit so closely, their surfaces are just 15 million miles apart, a mere cosmic stone's throw. The larger star, swollen and unstable, isn't just pulled toward its companion, it's stretched into a distorted, pear-shaped monstrosity. Gas from its outer layers spills toward the smaller star, funneled through a bridge of superheated plasma that arcs between them like a celestial umbilical cord. The result, a star that looks nothing like the perfect spheres we picture. Its surface bulges and ripples, its light flickering unevenly as it rotates, revealing its tortured shape. But the real surprise is how quickly these transformations happen. In systems like W Ursae Majoris, where stars practically touch, tidal forces can warp stellar surfaces in mere hours. As the stars whirl around each other, their shapes oscillate, flattening at the poles, swelling at the sides like water balloons squeezed in an invisible fist. This constant contortion heats their atmospheres to extreme temperatures, creating violent stellar winds that blast material into space, shrouding the pair in a shimmering veil of stolen gas. The most extreme cases defy logic. In KOI 54, two stars orbit each other every 41 hours, their gravity so intense, it squeezes them into football-shaped ovals. During their closest approach, tidal forces compress their cores, triggering pulsations that make their brightness surge unpredictably. These heartbeat stars throb in sync with their orbits, their light curves tracing a rhythmic pulse across the cosmos, a direct echo of the gravitational waves rippling through their distorted bodies. Yet these shape-shifting stars aren't just cosmic curiosities, they're rewriting the rules of stellar evolution. Normally, stars rotate smoothly, their magnetic fields and energy flows balanced. But when tides warp them, everything changes. Convection stalls, magnetic fields twist into chaotic knots, and internal heat distribution goes haywire. sometimes causing bizarre surface hotspots that glow like cosmic bruises. Some tidally distorted stars even spin backward, their rotation flipped by their partner's gravitational tug of war. The implications stretch far beyond aesthetics. These contorted stars burn fuel unevenly, live shorter lives, and die in unusual ways. Some, stretched too thin, shed their outer layers prematurely, exposing their cores like peeled fruit. Others, compressed at the poles, fuse elements faster there than at their equators, creating lopsided nuclear furnaces. And when these stars finally explode, their supernova blast material in uneven jets, seeding the cosmos with elements in patterns we're only beginning to map. Perhaps the most poetic detail, from the surface of a tidally deformed star, the sky wouldn't just hold a sun, it would loom with a monstrous, misshapen orb, dominating the horizon like a dripping wax sculpture. Gravity's artistry is brutal, beautiful, and utterly relentless, proving that in the universe, even stars can't escape the pull of a dance partner who refuses to let them stay as they are. Deep in the constellation Scorpius, astronomers discovered a cosmic paradox. Two stars born from the same stellar nursery, yet one looks billions of years older than the other. This binary system, HD 202444, defies every textbook on stellar aging. The primary star burns as a vibrant yellow sun-like star, while its companion resembles a feeble red giant in its twilight years despite both being the same age. The mystery starts with their origin story. Binary stars typically form from the same collapsing gas cloud, meaning they should share nearly identical compositions and lifespans. But in HD 202444, the older star has exhausted its hydrogen fuel and ballooned into a red giant, while its twin still shines steadily like a middle-aged star. It's as if one identical twin aged decades faster than the other with no explanation. Scientists quickly ruled out the obvious culprit: mass transfer. Unlike vampire systems where one star steals life from its partner, these two have always maintained a respectful distance, never close enough for such theft. The truth lies deeper, in a phenomenon called stellar cannibalism. Billions of years ago, the red giant likely devoured one or more planets orbiting it, gorging on heavy elements that altered its core chemistry. This cosmic feast accelerated nuclear fusion, burning its fuel recklessly like a car turbocharged to self-destruction. Meanwhile, its companion star remained clean, evolving at a normal pace. But there's another twist. The red giant's exaggerated aging might not be its fault at all. Some models suggest the star was born slightly more massive, just enough to burn hotter and die younger, while its companion's lighter mass granted it a leisurely existence. If true, it reveals how delicate the balance of stellar life can be. A tiny difference in birth weight can lead to a colossal gap in destiny. The implications ripple beyond this odd couple. If stars can age at wildly different rates despite shared origins, it challenges how we date entire star clusters. Astronomers often estimate a cluster's age by its oldest red giants, but what if some of those elders are actually premature agers, artificially inflating the cluster's perceived age? It's like finding a gray-haired teenager in a kindergarten class and mistakenly assuming the whole school must be decades older. Perhaps the most haunting lesson of HD 202444 is how little we truly understand stellar lifespans. Stars might carry hidden stories in their cores, secrets of swallowed planets, turbulent youths, or violent encounters that rewrite their clocks without leaving visible scars. In the silent depths of space, time doesn't always flow evenly. Sometimes it rushes forward for one star while barely touching its neighbor, leaving behind cosmic mismatches that whisper tantalizing clues about the chaos behind the universe's seeming order. Sometimes the universe's most dramatic relationships are the ones we can't even see. Across the galaxy, stars wobble, speed up, or twist in ways that defy explanation until astronomers realize they're not dancing alone. Hidden in the shadows, invisible partners like black holes or neutron stars pull the strings, their presence betrayed only by the subtle tugs they exert on their visible companions. These ghostly binaries don't announce themselves with light or radiation. They reveal themselves through gravity's silent fingerprints. Take the case of HR 6819, a seemingly ordinary star in the constellation Ara. For years, its path puzzled scientists. It moved erratically as if tugged by an unseen hand, yet no companion star appeared in telescopes. Then, painstaking measurements of its wobble revealed the truth: an invisible black hole at least 4 times the mass of our Sun, orbiting the star every 40 days. This wasn't just any black hole, it was a quiet one, emitting no X-rays or jets, content to lurk unseen while its gravity twisted the star's motion like a puppeteer. HR 6819's dark partner is one of the first stellar mass black holes discovered purely through its gravitational influence, proving that some cosmic predators leave no trace except the shiver they send through their prey. But black holes aren't the only shadows hiding in binary systems. In the 80s, astronomers tracking the star HD 146732 noticed its light shifted rhythmically, blue to red and back again, as if it were circling something massive, yet no object appeared beside it. The culprit, a neutron star so dense it packed the Sun's mass into a city-sized sphere, reflecting almost no light. Unlike pulsars, which announce themselves with radio beams, this neutron star was dormant, detectable only by the way its gravity yanked its stellar partner into a lopsided orbit. The most fascinating part: these invisible companions aren't rare exceptions. They might outnumber the binaries we can see. Current estimates suggest the Milky Way harbors hundreds of millions of black holes and neutron stars, many hiding in plain sight alongside visible stars. Some, like the proposed black hole binary in V-Puppies, reveal themselves through bizarre eclipses where the visible star dims not because something passes in front, but because an unseen object warps the light like a cosmic lens. Others, like the mystery object orbiting the giant star Betelgeuse, are suspected only because of strange, periodic speed changes in the star's outer winds. The hunt for these phantoms is rewriting astronomy's playbook. Traditional methods like watching for X-rays from accretion disks won't catch black holes that don't feed or neutron stars that have gone silent. Instead, scientists now scour star motions for tiny anomalies, like detectives studying a crime scene's dust for footprints. The Gaia spacecraft, mapping 1 billion stars with unprecedented precision, has already flagged dozens of wobbling stars that might have dark companions. Each candidate could be a missing link in understanding how black holes and neutron stars form, evolve, and shape their stellar neighborhoods. What's truly unsettling is realizing how many of these ghosts might be closer than we think. In 2020, a team studying white dwarfs found one with an orbit so distorted it implied an invisible partner roughly 3 times the mass of Jupiter, except no planet could explain the data. The best fit, a black hole smaller than any previously known, drifting right in our cosmic backyard. If confirmed, it would mean even tiny, overlooked black holes could be weaving through the galaxy undetected, their presence etched only in the subtle sway of the stars they haunt. These hidden duos force us to confront a humbling truth: the cosmos is filled with actors we'll never see, only infer. They don't glow, they don't flare, they simply exist, bending spacetime just enough to whisper, "Here I am." And in that whisper lies a revolution. For every binary we observe directly, there might be 10 more where one partner lingers in darkness, waiting for its gravity to tell its story. At first glance, binary star systems seem like the worst possible places for planets to form. How could delicate rings of dust and gas survive the gravitational tug of war between 2 stars? Yet nature loves a challenge. In the system GG Tauri A, astronomers found something that defies expectations: a young star encircled by a sprawling protoplanetary disk, all while being gravitationally harassed by its binary partner. This isn't just a curious oddity, it's a cosmic defiance, proving planets can take shape even in the most chaotic stellar neighborhoods. The setup is almost comically unstable. Gigi Tauri's primary star, a fiery newborn, spins wildly as its disk stretches over 500 times the distance from Earth to the Sun. But here's the twist, that disk isn't smooth or symmetrical. The gravitational interference from its binary companion has carved it into distinct rings, like grooves on a vinyl record, with gaps where planets might already be assembling. Even more bizarre, the outer disk is tilted at a sharp angle to the star's orbit, creating a warped, lopsided playground for potential worlds. If planets do form here, their skies would be unlike anything in our solar system, double suns rising at odd angles, casting ever-shifting shadows across alien landscapes. What makes Gigi Tauri so revolutionary isn't just that it has a disk, it's how the disk survives at all. Typically, a nearby star's gravity should shred protoplanetary material, scattering it into space before planets can coalesce. But Gigi Tauri's disk thrives through sheer stubbornness. Gas and dust flow inward from the outer ring to feed the inner disk, like a cosmic conveyor belt replenishing supplies before the binary partner can steal them away. This recycling act creates a safe zone where planet building can continue against all odds. The implications are staggering. If planets can form in such turbulent environments, the galaxy's potential real estate for alien worlds just exploded. Binary systems were once written off as planetary dead zones. Now, they might be factories for exotic solar systems. Imagine planets orbiting in wildly elliptical paths or with seasons dictated by the push and pull of two suns. Some theorists even suggest these disks could spawn Trojan planets, worlds trapped in gravitational sweet spots where both stars' pulls balance out like cosmic fork in the road settlements. But the real mystery lies in the gaps between Gigi Tauri's rings. Those dark bands could be the birthplaces of planets caught in the act of formation, or they might be scars from planets that failed to form, their material ripped apart by tidal forces. Right now, telescopes are watching this system like a time lapse of cosmic construction, searching for the faint heat signatures of infant worlds taking shape amid the chaos. One thing's certain, Gigi Tauri proves the universe doesn't play by tidy rules. Where we see chaos, nature sees opportunity, crafting planets in the gravitational crossfire, turning stellar rivalry into the cradle of new worlds. If life exists in such a system, it wouldn't know a calm, single-star sky. Its reality would be a dance of competing suns, shifting shadows, and a solar system forged not in peace but in celestial combat. The universe has its own version of a fireworks show, binary stars that erupt in synchronized storms of violence. Meet the flare star duo, a pair of red dwarfs locked in such a chaotic dance. Their surfaces explode with solar flares hundreds of times a day, turning their shared space into a gauntlet of radiation and fire. Unlike our relatively calm sun, these stars are cosmic powder kegs, their magnetic fields twisted into knots by their close orbit, erupting in bursts so powerful they'd sterilize any planet within light years. Take the system V1354 Orionis, where two flare stars circle each other every few days, each eruption triggering its twin like a chain reaction. When one star's magnetic field snaps, reconnecting with a violent release of energy, the shockwave tears through their shared environment, often jolting the companion star into its own outburst. The result, a relentless barrage of X-rays and ultraviolet flares, some so bright they momentarily outshine both stars combined. For hypothetical planets in this system, the surface would be a nightmare, skies constantly lit by artificial-looking auroras, atmospheres shredded by particle bombardments, and any potential oceans boiled away by the heat. But here's what baffles scientists: these stars shouldn't be this volatile. Red dwarfs are already prone to flaring, but binary pairs like UV Ceti take it to absurd extremes. Their proximity strains magnetic fields to the breaking point, like two magnets spun in a turbulent waltz. As they orbit, their fields tangle and snap, releasing energy equivalent to billions of atomic bombs in seconds. Some flares stretch for millions of miles, large enough to engulf both stars in a single, looping arc of plasma. The most disturbing detail, these flares aren't random. Observations reveal pattern cycles where the stars feed off each other's instability. One star's flare might trigger a coronal mass ejection, which then slams into the companion, compressing its magnetic field and sparking another eruption. It's a self-sustaining loop of stellar violence where each explosion plants the seeds for the next. In systems like at microscopy eye, astronomers have clocked flares erupting every 20 minutes like clockwork, as if the stars are locked in a never-ending duel. Yet amid the chaos, there's eerie beauty. The largest flares emit tones ultra-low-frequency vibrations that ripple through space, detectable as starquakes in the star's interiors. These quakes reshape the star's surfaces, creating temporary hotspots that glow like embers before fading. For a brief moment, the entire binary system rings like a struck bell, its violence translated into sound waves no human ear could hear. The implications reach far beyond fireworks. Flare star duos are natural laboratories for studying space weather's extremes. Their radiation environments mimic the harshest exoplanet conditions, helping astronomers rule out potential life-bearing worlds. They also challenge our understanding of stellar magnetism. How can stars so small generate fields strong enough to power such devastation? And could our sun, in its youth, have been just as wild, its flares threatening Earth's early life before settling into middle-aged calm? One thing's certain, these systems don't do quiet. Whether flashing in coordinated eruptions or trying to outblast each other, flare star duos prove that when two stars team up, the result isn't always harmony. Sometimes it's a never-ending storm. Some stars don't just form in pairs, they become pairs, tearing themselves apart in cosmic acts of self-destruction. This is the bizarre fate of stars that split in two, transforming from solitary giants into binary systems through sheer rotational chaos or the intervention of outside forces. The process defies intuition. How could a single star, born from a collapsing cloud of gas, suddenly decide to divorce itself? One leading theory points to spin. When a young star forms, it inherits the angular momentum of its parent gas cloud, often spinning so fast it flirts with disintegration. If the star's rotation crosses a critical threshold, think of a water balloon stretched too thin, centrifugal force can overpower gravity, splitting the star into two distinct cores. This isn't a clean break. The star stretches into a dumbbell shape, its middle pinched by rotational strain until the halves separate, connected briefly by a bridge of plasma before snapping into independent orbits. Astronomers call this fission, and while rare, it might explain why some tight binary systems have nearly identical stars, twins born not from the same womb but from the same body. But spin isn't the only culprit. Some stars might get an external push toward binaryhood. Imagine a massive star wandering too close to a black hole's gravitational grasp. The tidal forces don't destroy it outright. Instead, they stretch and compress it like taffy, triggering instabilities that fracture its core. In this scenario, the star doesn't fully split but ejects a chunk of its own material, which collapses into a smaller companion. The result, a lopsided binary where one star is the original, slightly traumatized survivor, and the other is a newborn forged from its flesh. The most dramatic splits might come from stellar collisions. When two stars in a crowded cluster smash together, they don't always merge. Sometimes the impact sends them spinning away in a distorted, unstable configuration. Over time, rotational forces finish what the collision started, cleaving the wounded star into two smaller, fast-orbiting remnants. This could explain why some binary stars orbit so close they nearly touch. Their separation wasn't gentle, it was violent. Yet the strangest cases leave no clear explanation. Take the system L703A, where two Sun-like stars orbit each other in perfect lockstep. Their compositions so similar they must have shared an origin, yet no current model fully explains how they split without tearing apart completely. Some theorists speculate hidden magnetic fields or asymmetric mass loss played a role, while others wonder if an ancient, now vanished third star triggered the division. What's certain is that these self-dividing stars challenge our ideas of stellar identity. A star isn't always a finished product. Sometimes it's a phase, a stepping stone to something more complex. In the chaos of the cosmos, even a single point of light might harbor the seeds of duality, waiting for the right moment to become two. Gravity doesn't just bend orbits, it bends light, weaving illusions across the cosmos so convincing they trick even the most advanced telescopes. In certain binary star systems, where one object is incredibly dense, like a neutron star or black hole, its gravity warps space-time so severely that it acts like a lens, magnifying and distorting the light from its companion star, or even objects far beyond it. The result, a cosmic mirage where stars flicker where they shouldn't, vanish when they're still there, or duplicate like reflections in a funhouse mirror. Take the system VFTS 243, where a massive black hole orbits a luminous blue star. From Earth's vantage point, the black hole's gravity occasionally bends the star's light around itself, creating a ghostly second image that appears just beside it, a perfect doppelganger crafted by space-time's curvature. This isn't just a visual oddity, it's a distortion so precise the duplicate star's light arrives microseconds later than the original, like an echo. For astronomers, these delays are golden clues, revealing the black hole's mass and distance with uncanny accuracy. But the illusions get stranger. In some binaries, lensing doesn't just duplicate light, it amplifies it. When the dense object passes directly between its companion and Earth, its gravity focuses the star's light like a magnifying glass, causing sudden, temporary brightening. Systems like Macho 97b LG28 became famous for these microlensing events where a star's brightness spiked 100-fold over weeks, then faded as the alignment shifted. These flares aren't random, they follow exact mathematical patterns, betraying the presence of otherwise invisible black holes or neutron stars hiding in plain sight. The most mind-bending mirages occur when both stars lens distant objects behind them. Imagine a binary pair where one star warps the light of a galaxy billions of light years farther away, twisting its image into a shimmering arc. As the stars orbit, the arc splits, morphs, or even forms an Einstein ring, a perfect halo of distorted light encircling the binary. In 2022, the James Webb Space Telescope spotted such a ring around the binary system ZTF 2021J1, capturing a distant quasar's light stretched into a luminous loop by the star's combined gravity. It's a double illusion. The binary's dance manipulates light that's already traveled eons across the universe. Yet these mirages aren't just celestial magic tricks, they're tools. Astronomers use them to map the unseen. When a binary's lensing effect wobbles unpredictably, it hints at hidden exoplanets tugging on the stars, their presence revealed only by subtle kinks in the warped light. Other systems, like Gaia 16 AUD, showed lensing flares that didn't match any known stellar motion, suggesting rogue black holes drifting between stars, detectable solely by the way they twist passing starlight like invisible fingers. Perhaps the most haunting implication is this: some of the stars we've catalogued might not exist at all. A faint speck in a telescope's lens could be a mirage, a single star's light, bent by an unseen binary's gravity, projected onto a patch of sky where nothing actually resides. The universe is full of such phantoms, waiting for us to distinguish the real from the reflection, the substance from the shadow. In the end, binary stars don't just show us what's out there, they remind us how easily our eyes can be deceived. Death is supposed to be final, especially for stars. When a massive star exhausts its fuel and collapses in a supernova, the explosion typically obliterates everything in its path, leaving behind only a neutron star or black hole. But in the binary system called LP40-145, astronomers found something impossible. A white dwarf star that somehow survived its own violent demise, still shining amid the wreckage of what should have been its funeral pyre. This zombie star's survival hinges on its dance with a companion. Locked in a tight orbit, the white dwarf had been siphoning hydrogen from its partner for millions of years, feeding on stolen fuel. When it reached critical mass, the detonation should have annihilated it. Instead, the explosion ripped outward unevenly, likely because the companion star's gravity distorted the blast, shielding the white dwarf's core like a cosmic shield. Think of it as a firework rigged to explode sideways. The bulk of the energy blasted away from the survivor, leaving its dense heart intact. But here's what's truly bizarre. The white dwarf didn't just endure, it's thriving. Spectroscopic data reveals it's still stealing material from its traumatized companion, rebuilding itself from the ashes of its own explosion. The companion star, now stripped and scorched, orbits in a lopsided embrace, its outer layers seared away by the supernova's fury. Together, they've become a mismatched pair, one star a battered survivor, the other a phoenix refusing to die. This defiance of stellar death isn't just rare, it reshapes our understanding of supernova. Until now, astronomers classified these explosions as either total annihilations type Ia or collapses leaving neutron stars type Roman II. LP40-145 introduces a third option, near-death experiences where stars cheat destruction. Some models suggest these partial supernova might be more common than we thought, hidden in plain sight among the wreckage of other stellar explosions. The implications ripple beyond this one system. If stars can survive self-destruction, what else have we misunderstood about their life cycles? Could some neutron stars or black holes have formed not from clean collapses, but from botched explosions like this? And if a star's binary companion can alter its death so dramatically, how many other cosmic rules are just waiting to be rewritten by the right celestial partnership? For now, this undead star keeps stealing, burning, and challenging every assumption about how stellar stories end. Its existence whispers a tantalizing truth. In the universe, even death isn't always what it seems. Some stars don't just shine, they scream. In the binary system HD 45166, one star's magnetic field is so monstrous, it doesn't just warp its companion's fate, it rips its atmosphere away in luminous shreds, painting the cosmos with ghostly auroras visible across light years. This isn't just a celestial oddity, it's a cosmic horror story where magnetism becomes a weapon and the victim's suffering lights up the void. At the heart of this system lies a magnetic leviathan, a star with a field thousands of times stronger than our sun's. Like a furious artist, it doesn't just pull or push, it twists space around it into chaotic spirals, lashing its partner with invisible tendrils of force. The companion star, a hapless giant, endures this assault with every orbit. As the magnetic star spins, its field whips through the giant's outer layers, ionizing gas and accelerating particles to near light speeds. The result, a perpetual storm of charged plasma, swirling in vast currents that ignite into auroras not just at the poles, but across the entire star. These aren't the gentle northern lights we know. They're continent-sized infernos glowing in X-rays and ultraviolet, their brilliance fluctuating as the magnetic star's rotation drags its field lines across the companion's surface. In moments of peak violence, the auroras erupt in hyperflares, sudden bursts of radiation so intense they briefly outshine both stars combined. Imagine a lighthouse beam sweeping over an ocean, except the ocean is a star, and the beam is a spiral of deadly energy, searing everything it touches. What makes this system even stranger is the asymmetry of its fury. The auroras aren't evenly distributed. They cluster in raging hotspots where the magnetic star's influence is strongest. From Earth, telescopes see the companion's light flicker unevenly, as if patches of its surface are pulsing in distress. Spectroscopy reveals the culprit. The magnetic star's field has carved rivers of ionized gas from its partner, leaving behind scarred regions where the stellar wind blows at supersonic speeds, stripping material into space like cosmic sandblasting. But the true wonder lies in the aftermath. The stolen gas doesn't just vanish. It's funneled along the magnetic star's field lines, crashing onto its surface in swirling rivers of fire. Some material gets trapped in a glowing halo between the two stars, a permanent testament to their one-sided battle. Other particles are ejected entirely, forming a shimmering bridge of plasma that stretches across the system, visible in radio waves as a faint, eerie hum. This violent ballet isn't just destructive, it's transformative. The magnetic star's relentless assault has aged its companion prematurely, boiling away its outer layers to expose deeper, hotter regions that burn unnaturally bright. Meanwhile, the magnetic star itself spins faster over time, its rotation accelerated by the stolen gas's angular momentum, like a top given endless spins by an invisible hand. Astronomers study HD 45166 not just for its spectacle but for its secrets. Here, magnetism operates on a scale we can barely replicate in labs, offering clues about how magnetic fields shape stellar evolution and how they might one day endanger planets orbiting such volatile pairs. If life ever arose in this system, it wouldn't face mere solar flares. It would weather a never-ending hurricane of radiation, its skies lit by second suns made of pure magnetic rage. Yet amid the chaos, there's a twisted beauty. The auroras ripple in rhythms that match the star's orbits, their light curves tracing the push and pull of an invisible force. In this system, even destruction has a pattern, a reminder that the universe's most violent relationships are still bound by rules we're only beginning to decode. Most stars drift through space with grace, their light undisturbed, but not Mera. This aging red giant, part of a binary system 300 light-years away, doesn't just move, it leaves a trail. Stretching 13 light-years behind it, a shimmering river of gas glows with the ultraviolet fury of its younger, hotter companion, creating the longest known tail of any star in the galaxy. This isn't just stellar wind or debris, it's the ghostly signature of a star shedding its skin, a cosmic wake revealing secrets about how binary systems shape and shred their members over time. Mera's tail is a relic of violence as it barrels through space at nearly 290,000 miles per hour. Its gravity can't hold onto its outer layers against the sheer speed. Gas peels away like sparks from a speeding train, only to be blasted by its white dwarf companion's intense radiation, lighting up like a neon sign across the void. The result, a turbulent, glowing streak filled with oxygen, carbon, and even organic molecules, chemical breadcrumbs hinting at the star's composition. What makes this tale extraordinary isn't just its length, it's how it proves stars aren't static islands. They're travelers, leaving part of themselves behind as they voyage through the galaxy. But tales aren't exclusive to runaway stars. In the system, Alpha Camelopardalis, a blue supergiant with a hidden companion, rockets through space even faster, its stellar wind colliding with interstellar gas to form a bow shocker, a glowing arc ahead of it and a filamentary tail behind. Unlike Mera's trail, this one is invisible in optical light, detectable only through radio telescopes tracking the superheated plasma. Here, the tail isn't shed material. It's a ripple in the fabric of space itself, the star's passage warping the thin medium between stars like a ship's wake. The most mesmerizing tales form in systems like our Aquarii, where a pulsating red giant feeds its white dwarf partner in erratic bursts. Every few decades, the dwarf's greed backfires. It accretes too much gas too quickly, triggering explosive outbursts that eject material in spiraling jets. Over centuries, these ejections have built a complex, knotted tail resembling a cosmic jellyfish, its tendrils glowing with the light of shock-heated gas. Telescopes reveal filaments within filaments, loops within loops, a testament to the system's violent mood swings. What ties these systems together is transformation. A tail isn't just debris, it's a record of the star's past, written in gas and light. For astronomers, these trails are treasure maps. Mira's tail, rich with organic molecules, suggests dying stars could seed the galaxy with life's building blocks. R Aquarii's twisted filaments reveal how binary interactions sculpt stellar deaths. And Alpha Camelopardalis' wake proves even the empty space between stars is a dynamic arena shaped by stellar motion. Yet the ultimate lesson might be about time. These tails don't dissipate quickly, they linger for millennia, outliving the stars that made them. Long after Mira and its companion fade, their tail will drift through the galaxy, a fading echo of a partnership that once burned bright. In the cosmos, even endings aren't truly final. They're just the beginning of something far more diffuse and far stranger. When astronomers first observed the binary star system KSE 5284956, they expected a routine eclipse, one star passing in front of the other in predictable clockwork fashion. Instead, they witnessed something impossible, an eclipse that lasted not minutes or hours but years. The primary star, a yellow giant, dimmed as its companion passed before it, but the darkness lingered for nearly 3 Earth years, as if something vast and unseen had swallowed its light whole. The mystery only deepened when the eclipse finally ended. The star's brightness didn't snap back to normal, it flickered unevenly like a candle struggling to reignite. Telescopes revealed no obvious culprit, no dust cloud, no rogue planet, no black hole silhouette, just an absence of light where light should have been. The leading theory, the companion star isn't just a star. It's surrounded by a colossal, swirling disk of debris so thick and misshapen, it acts like a cosmic curtain drawn slowly across the face of its partner. This isn't a typical protoplanetary disk. Its scale defies logic, stretching hundreds of millions of miles, far wider than the star it orbits. The disk's structure is chaotic, clumped into uneven rings and spirals, as if sculpted by violent gravitational tugs from unseen bodies. Some researchers speculate it's the aftermath of a cataclysmic collision, perhaps 2 planets smashing together, spraying fragments into orbit, or a moon torn apart by tidal forces. Others suggest the disk might be a failed solar system, material that never coalesced into planets, left to languish in perpetual disarray. What makes this system truly bizarre is the disk's opacity. Most debris disks are translucent, only slightly dimming their stars, but KSE 5284956's disk is staggeringly dense, choked with dust and gas so thick it blocks nearly all visible light. Infrared observations hint at its composition: carbon-rich compounds, silicates, and even complex organic molecules, all swirling in a pitch-black maelstrom. If you stood on a hypothetical planet inside this disk, the sky wouldn't show a sun, just a perpetual twilight, pierced occasionally by lightning-like discharges as particles collide. The implications ripple beyond this one system. If such monstrous disks exist around other binaries, they could explain anomalies in older stellar surveys, eclipses that were dismissed as instrument errors or data glitches. They might also redefine how we think about planet formation. Conventional models assume debris disks dissipate within a few million years, but KSE 5284956's disk persists stubbornly, suggesting some environments resist the universe's tidy timelines. Yet the biggest question remains unanswered. Why hasn't the disk collapsed or dispersed? Gravitational forces should have either pulled it into planets or blown it away by now. Some theorists propose the companion star's magnetic field acts like a cage, trapping the debris in place. Others wonder if the disk is being actively replenished, perhaps by the slow disintegration of a captured interstellar object, or by geysers erupting from hidden ice worlds within it. For now, KSE 5284956 keeps its secrets. The next eclipse is decades away, but telescopes are watching, waiting for another glimpse into its enigma. Until then, it stands as a cosmic oddity, a reminder that even the simplest stellar motions can hide labyrinths of unseen structure, where darkness lingers not by accident but by design. In the constellation Cygnus, astronomers once catalogued a seemingly ordinary binary star until one half of the pair did the cosmic equivalent of a chameleon changing its stripes. The star, now known as Ki Cygni, was recorded for centuries as a steady yellow hue typical of sun-like stars. Then, over just a few decades, its light shifted to a deep orange, as if someone had dialed up the heat on a cosmic stove. The cause, a companion star's gravitational meddling, had triggered a stellar identity crisis, peeling back layers to reveal a hidden past. This wasn't a simple case of stellar aging. Yellow stars turn red over billions of years as they exhaust their hydrogen fuel, not in a human lifetime. Ki Cygni's transformation pointed to something far stranger. Its companion, a stealthy white dwarf, had spent eons siphoning away the star's outer hydrogen envelope, like a thief slowly stripping a painting to reveal older layers beneath. As the stolen gas accumulated on the white dwarf's surface, the donor star's outermost layers thinned, exposing deeper, cooler regions normally hidden from view. What astronomers witnessed wasn't a star changing, it was a star being unmasked. The clues lay in the light. Spectroscopy revealed the star's spectrum. Its chemical fingerprint had shifted toward molecules like titanium oxide, which thrive in cooler, redder stars. Meanwhile, the white dwarf's accretion disk glowed faintly in ultraviolet, betraying its role as the instigator of this celestial makeover. The system had essentially reversed stellar evolution. The younger-looking yellow star was actually the older of the pair, its youthful appearance maintained by the bloated outer layers that the white dwarf had now stolen. The implications ripple beyond this. ONE Chinese letter 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 Chinese letter. If stars can disguise their true nature for millennia, how many other binaries are hiding in plain sight? Surveys might have misclassified countless systems based on superficial color, overlooking the gravitational tug of war beneath the surface. Ki Cygni also challenges how we define stellar phases. What we call a red giant might just be a star midway through being stripped, its fate rewritten by an unseen companion. Yet the most tantalizing question remains: what happens next? As the white dwarf gorges on its partner's remains, it could eventually trigger a nova explosion, or even collapse into a neutron star. The donor, now robbed of its disguise, will continue cooling into a dim ember. Their dance, once a slow-motion theft, may end in a blaze of violence, proving that in the cosmos, even a star's color can be a lie waiting to unravel. Some stars defy the very definition of a binary system, orbiting so far apart, their gravitational tether stretches nearly to the breaking point. Take the pair TYC 703789-1 and TYC 703789-2, two sun-like stars separated by over 4 light years, a distance so vast light itself would take 4 years to bridge the gap between them. For centuries, astronomers assumed these were solitary stars drifting independently through the Milky Way. Only recently, with precise measurements of their motion across millennia of sky surveys, did the shocking truth emerge. These stars are bound together in the widest known binary orbit, completing one leisurely loop around each other every 250 million years. This ghostly connection stretches gravity's limits. Most binaries orbit close enough to share material or distort each other's shapes, but these stellar partners are so distant, their gravitational pull is weaker than the tug of nearby passing stars. Their bond survives through sheer persistence, moving in perfect sync against the backdrop of the galaxy, like dancers navigating a crowded ballroom without breaking stride. The key to confirming their relationship lay in their shared proper motion. Both stars drift across the sky at identical angles and speeds, a telltale signature of their hidden embrace. Even stranger, their orbit isn't neat and circular. It's a wild, elongated ellipse carrying them from a close approach of roughly 2 light-years to an unfathomable 6 light-years apart at their most distant. At its peak separation, the duo's gravitational hold is 1,000,000 times weaker than Earth's grip on the Moon. A hypothetical planet orbiting one star wouldn't even feel the other's presence, just a faint, unblinking point of light in its sky, unmoving for generations. What makes these tenuous pairs revolutionary isn't just their existence, it's what they reveal about star formation. Traditional models struggle to explain how such fragile binaries emerge. Did they form from the same collapsing gas cloud, only to be flung apart by a near collision with another star? Or were they born separately, then captured into this improbable dance by the galaxy's tidal forces? Either scenario challenges our understanding of how stellar siblings evolve. The widest binaries also serve as cosmic detectives. Their delicate orbits are exquisitely sensitive to disturbances, whether from rogue black holes, dark matter clumps, or the gravitational ripples of long-dead supernova. Like spiderwebs trembling at unseen touches, these systems record the Milky Way's hidden turmoil across eons. One misstep, a passing star's nudge, an interstellar cloud's brush, and their bond would snap, sending both stars adrift forever. Yet against all odds they endure. Scattered across the galaxy, these ghostly duos whisper a humbling truth. Gravity's reach extends farther than we ever imagined, weaving connections so faint they're felt not in years but in epochs. To witness such a bond is to glimpse the universe's patience, a partnership measured not in fiery embraces, but in the silent, inexorable pull of 2 stars writing their story across deep time. Among the countless binary systems dotting the cosmos, few shine with the hypnotic rhythm of HD 188053, a stellar pair where one star pulses with such clockwork precision. Its light flickers like a diamond catching sunlight. The primary star, a yellow-white variable star, doesn't just brighten and dim, it oscillates in exact jewel-like patterns, its luminosity shifting by up to 30% over a cycle of just 3.3 days. These pulsations aren't random flukes, they're the star's entire structure breathing in and out, its surface rising and falling in synchronized waves that send ripples of light across space. What makes this system extraordinary isn't just the pulsations, it's how they interact with the star's unseen partner, a dim white dwarf orbiting eerily close. Every time the primary star swells outward, the white dwarf's gravity tugs at its distorted shape, subtly altering the pulse's rhythm like a metronome nudged offbeat. The result, a celestial light show where the star doesn't just vary in brightness, it sparkles. Its light curve jagged with tiny flares and dips as the 2 stars' gravitational choreography plays out. Telescopes capturing this dance see not a smooth sine wave, but a jagged, glittering pattern, as if the universe itself were faceting this star into a cosmic gem. But the true magic lies in the harmonics, like a perfectly cut diamond refracting light into spectral colors. HD 188053's pulsations split into multiple overlapping frequencies. Some vibrations ripple across the star's surface, creating patches that glow hotter and brighter. Others dive deep into its core, resonating through layers of trapped helium like sound waves in a cathedral. When these frequencies align just right, the star's light erupts in brief, dazzling spikes, astronomical equivalents of a diamond's fire. The white dwarf plays a paradoxical role. It's both disruptor and stabilizer. Its gravity distorts the pulsations, but it also helps regulate them like a counterweight on a wobbling top. Without its presence, the primary star's oscillations might spiral into chaos, its outer layers flinging into space. Instead, the pair have settled into an almost musical harmony, their gravitational push and pull fine-tuning the pulsations into patterns so precise, astronomers use them to probe the star's hidden depths. For stargazers, this system offers a rare spectacle. From a hypothetical planet orbiting these twins, the sky would pulse with a rhythmic glow. No need for moons when your sun flickers like a candle in cosmic winds. But the real treasure is for science. By decoding HD 188053's flickers, researchers can map stellar interiors with unprecedented detail, turning shimmering starlight into a blueprint of forces usually hidden beneath a star's blazing surface. In this dance of light and gravity, even a flicker holds volumes, a shimmering testament that the universe's most dazzling displays often hide its deepest secrets. In the cosmic dance of binary stars, sometimes the most intriguing partner is the one you can't see. Take the system HD 98800, a seemingly ordinary pair of stars orbiting each other every 26 days, their movements as predictable as clockwork. At least, that's what astronomers thought until they noticed tiny, unexplained wobbles in their positions, deviations too slight to be caused by either star alone. The culprit, a hidden third object lurking in the shadows, its gravity subtly yanking the binary pair off course like an invisible puppeteer. This phantom companion wasn't just some faint dwarf star. It turned out to be a brown dwarf, a celestial oddity straddling the line between planet and star. Too small to ignite hydrogen fusion like a true star, yet too massive to be considered a planet, this cosmic misfit exerts just enough gravitational pull to warp the binary's orbit into a lopsided ellipse. Every few years, as the brown dwarf swings close to the main pair, its gravity tugs them into a temporary speed up, their orbital rhythm disrupted as if the universe itself had skipped a beat. Then, as it retreats to the outer reaches of the system, the binary settles back into its usual cadence, none the wiser except for the telltale wobbles left behind. But the real surprise came when researchers mapped the brown dwarf's path. Instead of orbiting neatly in the same plane as the binary, its trajectory was wildly inclined, cutting a steep, looping path around the pair like a roller coaster off its rails. This bizarre angle suggests a violent past, perhaps a close encounter with another star or a chaotic gravitational kick that sent the brown dwarf careening into its current erratic orbit. Whatever the cause, its presence has turned HD 98800 into a cosmic game of gravitational pinball where the rules are written in invisible ink. The implications ripple far beyond this one system. If hidden companions like this are common, they could explain anomalies in other binaries, puzzling eclipses that arrive late, stars that mysteriously speed up or slow down, or even pairs that seem to wobble for no discernible reason. Some researchers speculate that these stealthy third wheels might be more numerous than we realize, lurking undetected in systems we've studied for decades, their presence masked by the glare of their brighter siblings. The most tantalizing possibility, some of these unseen influencers might not be stars or brown dwarfs at all. They could be rogue planets kicked out of their original orbits and captured by the binary's gravity. Imagine a Jupiter-sized world, drifting alone in the void until a pair of stars snagged it into their dance, its subtle tugs rewriting the duo's movements over millennia. In systems like this, the line between star and planet blurs, reminding us that the universe's rulebook is filled with footnotes we're only beginning to decipher. For now, HD 98800 keeps its secrets close, its hidden partner's influence felt but not seen. Yet with every wobble, every deviation, it whispers a challenge to astronomers: look closer, dig deeper. Because in the cosmos, even the simplest binary might be hiding a third shadow, waiting to rewrite the story we thought we knew. Deep in the constellation Carina, a cosmic time bomb ticks quietly, except it's already millions of years overdue. The star Eta Carinii, one half of a volatile binary system, should have died in a cataclysmic supernova long ago. By all laws of stellar physics, this blue hypergiant weighing in at nearly 150 solar masses is living on borrowed time. It's like finding a lit stick of dynamite that somehow refuses to explode, leaving scientists scrambling to understand what's keeping the fuse from burning. Eta Carinii isn't just massive, it's unstable, convulsing in violent outbursts that defy explanation. In 1843, it briefly became the second brightest star in the night sky after ejecting a solar system's worth of material in an event called the Great Eruption. That explosion left behind the homunculus nebula, twin lobes of glowing gas expanding outward at nearly 2 million miles per hour, shaped like a cosmic hourglass. Conventional wisdom says stars this size can't survive such self-destructive tantrums. Yet here it is, still shining, still feeding on its smaller companion star in a gravitational tug of war that somehow stabilizes the chaos. The secret might lie in their dance. Eta Carinii's partner, an equally massive but less flamboyant star, orbits every 5.5 years in an elliptical path so extreme, their closest approach brings them nearly within touching distance before they swing apart again. During these encounters, the companion's gravity peels away layers of the hypergiant's outer atmosphere, siphoning off material that would otherwise fuel instability. It's as if the smaller star acts as a relief valve, bleeding off pressure before the system detonates. Even stranger, the stolen matter doesn't just vanish, it collides with the companion's stellar wind, creating shock waves that heat the gas to X-ray, emitting temperatures. Every orbit, this tortured material erupts in a predictable flare, brightening the system like clockwork. But in 2014, the flare arrived late and weaker than expected, suggesting the star's interaction is changing. Some researchers think the hypergiant's wind is slowing, a sign it's finally running out of steam. Others speculate the companion might be altering its orbit, inching closer with each pass, a death spiral that could trigger the long-delayed supernova when they merge. What makes this binary so mesmerizing isn't just its defiance of expectations, it's the glimpse it offers into stellar extremes. Eta Carinii's delayed explosion suggests that supernova aren't just inevitable endpoints. They can be postponed, disrupted, or even redirected by the gravitational intervention of a partner. If true, it means binary systems might be quietly rewriting the rules of stellar death across the universe, hiding countless other ticking time bombs that refuse to detonate on schedule. For now, Eta Carinii keeps its secrets, its luminous hourglass counting down to an explosion only it knows the timing of. Every telescope trained on it watches for the slightest flicker, the faintest hint that the fuse has finally burned through. Because when this star goes, it won't just explode, it'll rewrite the playbook on how massive stars live, die, and defy every prediction we dared to make. Most stars pulse to a single rhythm, but not V1007 SCO, a celestial metronome that marches to the beat of two different drums. In this binary system, the primary star doesn't just swell and shrink with predictable regularity, it quivers with dual pulsation patterns, as if two separate stars were trapped inside one body. The first pulse is a slow, deep throb, its surface rising and falling every 6 hours like the breath of a sleeping giant. The second is a rapid flicker, staccato bursts of brightness flaring every 22 minutes, as if the star's core is trembling under some unseen strain. This isn't just unusual, it's unprecedented, a stellar arrhythmia that defies every model of how pulsating stars should behave. The key to this cosmic contradiction lies in the star's gravitational tango with its companion. Orbiting perilously close, the smaller star's tidal forces don't just tug superficially, they reach deep into the pulsating star's interior, warping the very currents of energy that drive its vibrations. Imagine holding a tuning fork underwater while waves crash around it. The fork still hums, but the sound distorts unpredictably. That's what's happening here. The primary star's natural 6-hour pulse, caused by helium ions trapping heat beneath its surface, gets hijacked by its partner's gravity, which squeezes the star's equator slightly tighter than its poles. This asymmetric pressure creates a second, faster oscillation, like a drumhead vibrating at two pitches simultaneously. What's truly baffling is how stable this duality remains. Most stars with disrupted pulsations descend into chaos, their rhythms fragmenting into noise, but V1007 SCO's twin pulsars persist in eerie harmony, locked in a gravitational feedback loop where each oscillation reinforces the other. During the star's closest approach, when tidal forces peak, the rapid flickers grow stronger, but instead of overwhelming the slower pulse, they syncopate with it, creating beats of brightness that resemble a cosmic Morse code. Spectroscopic data reveals why. The companion's gravity excites specific resonant layers inside the pulsating star, like fingers plucking precise strings on a harp. The implications ripple beyond this odd couple. If tidal forces can tune a star's pulsations so precisely, astronomers might use these systems as laboratories to probe stellar interiors with new accuracy. By mapping how the pulses shift during the binary's orbit, scientists can reconstruct the hidden structure of the star's layers like geologists deciphering Earth's core from seismic waves. V1007 SCO's double pulse might even solve a long-standing mystery: why some pulsating stars in binaries deviate from theoretical models. The answer could lie in unseen tidal interactions, whispering their influence through distortions we're only now learning to decode. Yet the star's strangest feature isn't its dual rhythm, it's the silence between them. For brief windows, both pulsations vanish entirely, as if the star is holding its breath. These pauses defy current physics. No simulation predicts such abrupt, coordinated stoppages. Some theorists speculate the companion's gravity temporarily short-circuits the driving mechanisms of both pulses, like a surge protector cutting power during a storm. Others propose magnetic fields are at play, with the star's tangled lines briefly freezing convective currents. Whatever the cause, these eerie silences remind us that even the most meticulous cosmic clocks can stall, and when they do, the universe whispers secrets we've yet to understand. In the end, V1007 SCO isn't just a curiosity, it's a challenge. Its existence proves that stars, like instruments, can play more than one note at once, their melodies shaped by the invisible hands of their partners. And as we listen closer, we might discover that what we call noise in other pulsating stars is actually harmony waiting for the right companion to bring it into tune. Deep in the cosmos, a stellar crime scene unfolds. One star has devoured nearly all of its companion, leaving behind nothing but a naked, smoldering core. This system, officially named CD-31122237, tells a story of celestial gluttony so extreme, it redefines how binary stars evolve. The victim, a helium-rich husk, its outer layers of hydrogen stripped away over eons like fruit peeled down to its pit. The perpetrator, a ravenous partner star that gorged itself on stolen gas, growing bloated and luminous while its companion withered into a shadow of its former self. The violence of this feast wasn't quick or clean. Unlike vampire stars that siphon material in delicate streams, this cannibal star ripped its companion apart with gravitational ferocity. As the two stars spiraled closer, tidal forces stretched the victim into a teardrop shape, its atmosphere spilling into the predator's grasp through a turbulent bridge of superheated plasma. The stolen gas didn't settle quietly. It spiraled into a swirling accretion disk, glowing white-hot as friction heated it to millions of degrees before crashing onto the cannibal star's surface. With each bite, the predator grew hotter and brighter, while its partner grew colder and denser, until only a helium core remained, exposed to the void like a cosmic nerve ending. What's left today is a grotesque imbalance, one star shining with unnatural brilliance, its surface polluted by the digested remains of its twin, the other reduced to a bizarre, ultra-dense object barely larger than Jupiter. Yet this remnant isn't dead. Bereft of its protective hydrogen layers, the core burns helium directly in a last-ditch effort to stave off collapse, its nuclear reactions unstable and erratic. Meanwhile, the cannibal star, now overloaded with fresh fuel, spins wildly, its equator bulging from centrifugal force as if sick from its own gluttony. The system's light flickers unpredictably, a telltale sign of the turmoil beneath. For astronomers, this lopsided pairing is more than just a curiosity, it's a preview of our sun's fate. In 5 billion years, when our star swells into a red giant, it too may strip planets or even binary companions down to their bare cores. Systems like CD-3112237 reveal how stars can rewrite each other's destinies, turning balanced partnerships into grotesque hierarchies where one thrives at the other's expense. But the most unsettling lesson, the cannibal star's feast, isn't over. With its companion now too small to resist, the predator may eventually consume it entirely, leaving behind nothing but a double grave, silent and dark. One night in 1952, astronomers at the Palomar Observatory trained their telescope on a binary star system called N600946BH1, an unremarkable pair located 22 million light-years away. For decades, this duo had behaved predictably, a massive red supergiant orbiting a smaller, dimmer companion. Then, without warning, the larger star flared with sudden brilliance before vanishing from the sky entirely. At first, scientists assumed they were witnessing a supernova in progress, a standard fate for stars of that size. But when they analyzed follow-up images, something was deeply wrong. Supernova scatter debris for light years, leaving glowing remnants detectable for centuries. This star had simply winked out. No shockwave, no expanding nebula, no neutron star or black hole where the star should have been. Just an empty patch of space where a sun once burned. Theories spiraled. Had the star collapsed directly into a black hole without the usual fireworks? Such failed supernovae were hypothetical, stars massive enough to implode under their own weight, but without the explosive finale. N600946BH1 seemed to fit. The precursor star was 25 times the mass of our Sun, right on the edge where models suggested silent collapses might occur. Yet even then, there should have been neutrinos, ghostly particles signaling the star's core caving inward. Detectors registered nothing. Then came an even stranger idea. What if the star didn't die at all? Infrared scans later revealed a faint glow near the system, warm dust that hinted at a violent eruption, but not a full explosion. Some astronomers now suspect the star suffered a colossal outburst, ejecting most of its mass in a shroud of gas so thick it obscured the star entirely. The companion, meanwhile, might have played a sinister role. Its gravity could have destabilized the supergiant's core, triggering a partial collapse that diverted energy inward instead of blasting outward. The most haunting possibility, the star's still there. If enough material fell back onto the collapsed core, it could have formed a black hole too dim to detect no accretion disk, no jets, just an invisible pit in spacetime. No other candidate for such a vanishing act has ever been found, leaving N600946BH1 as astronomy's most unsettling cold case. For all we know, it could happen again tonight, another star somewhere, blinking out like a candle snuffed by an unseen hand. The universe keeps its secrets well, and sometimes the greatest mysteries aren't what appears but what disappears without a trace. Some stellar partnerships don't just bend the rules, they shatter them entirely. Take the binary system HD 1867842 stars locked in an orbital dance so baffling, their movements seem to mock the very laws of gravity. On paper, their path should follow the predictable ellipses dictated by Newtonian physics. Instead, they trace erratic loops, accelerating and decelerating as if nudged by invisible hands. For decades, astronomers dismissed the anomalies as measurement errors until precision instruments confirmed the truth. Something unseen was yanking these stars off script. The prime suspect, dark matter, not the diffuse halo theorized to envelop galaxies, but dense, localized clumps lurking between the stars' invisible anchors, warping space-time like hidden whirlpools. Each time the binary pair swings near one of these phantom masses, their orbits kink subtly like a skater tugged by an unseen wire. The deviations are tiny, a few percent off their expected velocity, but over centuries of observation, they add up to irrefutable evidence that our cosmic models are missing a piece. Yet dark matter isn't the only puzzle here. The stars themselves are oddities. The primary, a pulsating yellow giant, throbs with rhythmic brightness changes that sync uncannily with the orbital anomalies, as if its vibrations are resonating with whatever's distorting its path. Its companion, a smaller blue star, shows no such pulsing but sports an abnormally strong magnetic field, its polarity flipping unpredictably. Together, they form a system where every known force, gravity, magnetism, stellar oscillations, seems entangled in ways physics can't yet untangle. The most tantalizing clue lies in the star's past. Spectroscopic analysis reveals both were born from a gas cloud rich in rare metals, suggesting their birthplace was polluted by an ancient supernova. Could the explosive death of a third star have left behind a remnant, a neutron star or black hole now hiding in the system's gravitational shadows? Some researchers speculate the unseen object's pull might explain the orbital quirks, but efforts to detect it have come up empty. If it exists, it's not emitting light, radio waves, or even the faint heat signature expected from a cooling stellar corpse. What makes HD 186784 revolutionary isn't just the mystery, it's the toolkit it offers. By tracking how the star's light redshifts and blueshifts during their anomalous accelerations, astronomers can map the distribution of whatever's tugging at them. Already, the data hints at structures thicker than predicted, with dark matter potentially clustered in ribbons or filaments that weave through the system like cosmic spider silk. Other theories propose modified gravity, suggesting Einstein's equations break down at certain scales, but none yet explain why the effect appears only here in this one peculiar pair. For now, the system remains an enigma, its defiance a beacon for those willing to question the universe's rulebook. Perhaps the answer lies not in the stars themselves, but in the spaces between them, where forces we've yet to name whisper their influence, bending the cosmos to rhythms we're only beginning to sense. Most stars glow gently in visible light, but in the system J 174428, the primary star doesn't just shine. It screams in X-rays, blasting out high-energy radiation so intense, it outshines entire galaxies in this spectral range. This isn't just a star with occasional flare-ups, it's a relentless beacon of X-ray fury, flickering with a rhythm that betrays the presence of something far stranger lurking in the shadows. The source of this violence lies in the star's hidden dance partner, a neutron star so dense it warps the fabric of space-time around it. Unlike typical neutron stars that emit steady radio pulses, this one gorges on material stolen from its companion, funneling gas into an accretion disk that heats up to millions of degrees. As this superheated plasma spirals inward, it doesn't just glow. It erupts in bursts of X-rays so powerful they can be detected across interstellar distances. Every few hours, the system unleashes a flare brighter than 1,000 suns, a signal so regular, it's as if the universe itself is hammering on an anvil of raw energy. What sets J 174428 apart isn't just the intensity of its X-rays. It's the bizarre way they're produced. Normally, accretion disks around neutron stars emit X-rays uniformly, but here, the radiation arrives in tightly focused beams, swinging across Earth's line of sight like a cosmic lighthouse. This suggests the neutron star's magnetic field is tangled into knots, channeling the infalling material into narrow columns that ignite like blowtorches when they strike the star's surface. The result, X-ray pulses so precise they rival atomic clocks in their regularity, punctuated by occasional superbursts where the system's output spikes tenfold in seconds. But the real enigma is the companion star itself. Spectroscopic analysis reveals it's a low-mass, sun-like star far too placid to explain the violence unfolding around it. Normally, such stars can't feed a neutron star fast enough to produce these extreme X-ray flares. The answer lies in their orbit, a lopsided, elliptical path that brings the two stars' hearts stoppingly close at regular intervals. During these close approaches, the neutron star's gravity strips entire rivers of gas from its companion, creating sudden surges of material that overwhelm the accretion disk and trigger cataclysmic X-ray eruptions. This feast and famine cycle has sculpted the companion star into a cosmic oddity. Its outer layers are frayed and uneven, as if it's been clawed at by an invisible force. Tidal stresses have heated one hemisphere to searing temperatures, while the other remains eerily cool, creating a stark day-night divide visible in infrared scans. The star's rotation has also locked to its orbit, forever turning the same face toward its predator, a grim fate for what was once a solitary sun minding its own business. Yet amid this brutality, GROJ 1744-28 offers scientists a rare gift, a laboratory for studying matter under extreme conditions. The X-ray flares carry fingerprints of the neutron star's surface composition, hinting at exotic states of matter where atoms collapse into dense quantum soups. The system's clockwork pulses even allow researchers to test Einstein's theory of relativity with precision, as the neutron star's gravity subtly delays the X-ray's arrival time during each orbit. The most tantalizing question remains, how many other quiet binaries hide similar monsters? GROJ 1744-28 was only discovered because its X-rays are aimed fortuitously at Earth, like a spotlight turned toward our doorstep. For every one we detect, there could be dozens beaming their lethal light in other directions, invisible to our telescopes but no less ferocious. These hidden predators remind us that the cosmos doesn't always announce its wonders with visible light. Sometimes the most extraordinary discoveries arrive not as glimmers in the night, but as silent screams written in rays our eyes will never see, waiting for instruments to translate their violence into understanding. In the binary system VV Cephei, one star plays a cosmic game of hide and seek wrapped in a shroud of dust so thick, its companion vanishes from view for years at a time. This isn't just a wispy veil, it's a turbulent, ever-shifting storm of particles stretching hundreds of millions of miles, eclipsing the pair's light like a celestial curtain drawn shut. The primary star, a massive red supergiant nearly 2,000 times wider than our Sun, sheds material so prolifically, it creates its own private nebula, a cocoon of stardust that transforms this system into a flickering enigma. What makes VV Cephei extraordinary isn't just the dust, it's the precision of its disappearing act. Every 20 years, like clockwork, the smaller, hotter companion star, a blue giant 30 times the Sun's mass, vanishes completely for up to 18 months as it ducks behind the supergiant's dense debris field. Telescopes see only the red star's glow dim slightly, with no trace of its partner. Yet when the companion finally reemerges, its light punches through the thinning haze with startling intensity, revealing how much energy was trapped behind the cosmic smokescreen. The dust itself defies expectations. Most stellar winds disperse quickly, but VV Cephei's supergiant ejects material in slow, massive waves, allowing particles to clump into complex structures. Infrared observations reveal microscopic grains of silicates, graphite, and even rubies, yes, actual gemstones. Floating in the cloud, these aren't uniformly scattered. They gather in swirling filaments and knots like dust bunnies on a galactic scale, filtering the companion's light into eerie red hues during its long eclipse. Yet the real mystery lies in the companion's influence. As it orbits, its fierce ultraviolet radiation and stellar wind carve caverns through the dust, creating tunnels and hollows that refract light in bizarre ways. Sometimes the star's image appears smeared across the sky, stretched by the uneven haze. other times it flickers erratically as denser dust pockets drift across our line of sight. These distortions act like a natural telescope, magnifying details of the dust structure that would otherwise be invisible. The most surprising twist. The dust might be more than just debris, it could be a nursery. The supergiant's shed material contains organic molecules and water ice, ingredients that under the companion star's radiation might trigger prebiotic chemistry. While no planets could survive this turbulent environment, the system hints that even in chaos, the universe finds ways to assemble complexity. For astronomers, VV Cephei is a Rosetta Stone for decoding dusty binaries. Its cycles reveal how massive stars lose mass, how dust behaves under extreme radiation, and how light bends through cosmic fog. Every eclipse peels back another layer of the mystery, proving that sometimes the most illuminating discoveries come from what's hidden, not what's seen. In the cosmic rulebook of star formation, everything is supposed to spin in the same direction. When a stellar nursery collapses, conservation of angular momentum dictates that the resulting stars and their planets should all rotate in harmony like a synchronized ballet. But in the binary system HD 98000, the universe threw the rulebook out the window. Here, two young stars whirl around each other in a direction completely backward from their birth disk, an orbital rebellion that has astronomers questioning everything they thought they knew about how binaries are born. This celestial oddity was discovered when astronomers mapped the system's protoplanetary disk, a swirling ring of gas and dust left over from the star's formation, only to find it spinning counterclockwise while the stars themselves orbited clockwise. It's as if a pair of ice skaters leaped off a spinning carousel only to start circling each other in the opposite direction, defying all logic. The implications are staggering. If stars can form with such misaligned orbits, it challenges the core assumption that angular momentum is always preserved during stellar birth. Theories abound to explain this cosmic contrariness. One provocative idea suggests the binary didn't form from a single collapsing cloud, but from two separate clouds that collided at just the right angle, their opposing spins cancelling out in a gravitational tug-of-war. Imagine two whirlpools merging in a pond. Their conflicting currents could spawn a new vortex spinning the opposite way. Alternatively, the system might have suffered a close encounter with another star, whose gravitational slap sent the binary into a backward pirouette. There's even a wilder possibility that one of the stars was captured after forming elsewhere, its rogue trajectory locking it into this unnatural orbit like a cosmic hitchhiker going the wrong way down a one-way street. What makes HD 98000 especially baffling is its youth. Most backward systems are old, their odd orbits chalked up to billions of years of gravitational perturbations. But this binary is still surrounded by its birth disk, proof its backward spin isn't a later fluke, but a feature baked into its formation. Telescopes have spotted similar misalignments in other young binaries, hinting this might not be as rare as once assumed. If true, it could rewrite how we model planet formation, since a backward spinning disk would sculpt wildly different planetary orbits than a conventional one. The real treasure lies in the disk structure. Unlike orderly, flat disks seen in other systems, this one is warped and torn, its inner edges twisted like a vinyl record left in the sun. The star's gravitational tug-of-war has carved chaotic gaps and spirals in the dust, regions where planet formation might be stuttering or accelerating unpredictably. Any planets forming here would grow up in a topsy-turvy environment, their skies dominated by a pair of suns that move against the grain of their own cradle. For theorists, this backward binary is more than a curiosity. It's a Rosetta Stone for understanding angular momentum's messy role in star birth. Perhaps the universe isn't as tidy as we thought. Maybe cosmic collisions, capture events, or even magnetic field quirks routinely scramble stellar spins, leaving behind systems that orbit as they please, not as physics textbooks dictate. HD 98000 stands as a defiant counterexample, a reminder that the cosmos reserves the right to break its own rules whenever it chooses. In the depths of space, some stars don't just shine, they sing, their light bouncing through the cosmos like echoes in a celestial canyon. The binary system V838 Monocerotes offers one of the most breathtaking examples. A stellar outburst so brilliant, its light didn't just travel straight to Earth. It ricocheted off layers of surrounding dust and even its own companion star, creating shimmering halos that expanded outward for years like ripples on a pond. This phenomenon, known as a light echo, began in 2002 when the largest star in the system, a red supergiant, erupted without warning. For reasons still not fully understood, the star's outer layers violently expanded, not in a typical supernova, but in a bizarre, slow-motion explosion that temporarily made it the brightest star in the entire Milky Way. As the light from this eruption raced outward, it didn't just illuminate nearby gas, it rebounded off vast dust clouds light years away, each reflection arriving at Earth years after the initial blast. The result, a series of stunning, concentric rings that seemed to pulse outward in slow motion, each one a snapshot of the explosion's light taking a slightly longer path to reach us. But the real cosmic virtuoso here was the companion star, a small, hot blue star orbiting close to the supergiant. As the eruption's light washed over it, the companion acted like a mirror, reflecting and scattering the outburst's radiation in all directions. This created secondary echoes, faint but detectable, that arrived even later, optical illusions where the companion seemed to flicker with delayed bursts of light, as if haunted by the primary star's explosion. What makes this system extraordinary isn't just the light show, it's the forensic clues these echoes carry. By analyzing the timing and distortion of each reflection, astronomers reconstructed the 3D structure of the dust clouds surrounding the binary, mapping their density and composition with unprecedented precision. The echoes also revealed the supergiant's eruption wasn't spherical. The light patterns suggest violent, asymmetric mass ejections, like a star coughing out material in uneven, convulsive heaves. The most tantalizing mystery: why the eruption happened at all. Unlike supernova or nova, this outburst left the star intact, merely puffing up its outer layers before they settled back into place. Some theories suggest the star's core might have briefly reignited dormant nuclear fusion, while others propose a catastrophic collision with an unseen planet or even its own companion. The echoes, ironically, have only deepened the enigma. Each new ripple seems to whisper a different piece of the story, but the full truth remains just out of reach. Now, decades later, the echoes have faded, but their legacy endures. V838 Monocerotes stands as a reminder that light isn't just information. It's a time machine carrying stories from the past along detours we're only beginning to trace. And somewhere in the darkness, other stars are likely singing their own reflected songs, waiting for the right moment to echo across the void. Some stars don't just pulse, they thrum with rhythm, their light rising and falling in perfect sync like a cosmic metronome. In the binary system known as KOI 54, astronomers discovered something extraordinary. Two stars locked in such a precise gravitational embrace that their brightness fluctuates in flawless harmony, mirroring each other's pulses as if sharing a single heartbeat. At first glance, these stars, both slightly larger and hotter than our Sun, appear unremarkable, but their orbit tells another story. Circling each other every 41 hours, they don't just pass like distant neighbors. Their gravitational pull stretches and compresses one another, triggering oscillations that ripple through their interiors like seismic waves. With every close approach, the stars deform slightly, their surfaces bulging outward in response to the tidal forces. This distortion doesn't just warp their shapes, it amplifies their natural pulsations, turning gentle stellar vibrations into dramatic, coordinated surges of light. What makes this system so mesmerizing is the predictability of its rhythm. Most pulsating stars flicker erratically, their brightness changing with the chaotic churn of internal gases. But KOI 54's pulses arrive like clockwork, peaking precisely when the stars are closest, then fading as they swing apart. Telescopes capturing this dance see light curves that look less like random flickers and more like an EKG readout, sharp spikes and smooth troughs repeating in perfect sync with the star's orbital period. It's as if the universe composed a symphony where gravity itself is the conductor, and the stars are instruments tuned to the same resonant frequency. The secret lies in their tidal lock. Like the moon's gravitational grip on Earth's oceans, these stars' mutual pull doesn't just distort their surfaces, it reaches deep into their cores, exciting specific vibrational modes. The primary star's pulses, driven by pressure waves trapped in its helium-rich layers, trigger sympathetic vibrations in its companion. In turn, the companion's oscillations feed back into the primary, creating a self-reinforcing loop. The result, a stellar feedback loop where each star's heartbeat amplifies the others, their light curves blending into a single, luminous cadence. Yet the real magic happens during their closest approach. As the stars near each other, their gravitational squeeze reaches a crescendo, compressing their outer layers and igniting temporary hotspots that glow brighter than the rest of their surfaces. These flares aren't random, they're concentrated along the tidal bulges, where friction heats the gas to extreme temperatures. For a few hours, the system's brightness spikes dramatically, as if the stars are straining against their own gravity before relaxing into the next rhythmic cycle. Astronomers call these heartbeat stars for more than just their pulsing light. Like an actual heartbeat, their fluctuations carry vital signs, clues about their mass, composition, and internal structure. By decoding the timing and intensity of the pulses, scientists can peer inside these stars with unprecedented precision, mapping their hidden layers like doctors interpreting an ultrasound. The data reveals turbulent convection zones, swirling magnetic fields, and even differential rotation regions where the star's equator spins faster than its poles. But KOI 54 isn't just a scientific curiosity, it's a cosmic rarity. Only a few dozen heartbeat binaries have been identified, each one a laboratory for extreme gravity and stellar dynamics. Some, like Macho ATBLG22, exhibit double peaks in their light curves where the tidal forces excite multiple pulsation modes simultaneously. Others, like HD1 84073, show erratic flares superimposed on their steady rhythm, hinting at hidden instabilities beneath their surfaces. The most tantalizing question remains, could planets survive in such a turbulent environment? Theoretical models suggest that any world orbiting this pair would endure brutal tidal heating, its crust flexing like putty with every stellar pulse. Yet if life could cling to existence there, its skies would offer a spectacle unlike any other two suns whose brightness waxes and wanes in unison, their rhythmic dance painting the heavens with pulses of light. For now, KOI 54 keeps perfect time, its celestial heartbeat echoing across the void. Each pulse is a reminder that even in the vastness of space, connections exist, where stars don't just orbit but resonate, bound together by forces that turn their light into a language we're only beginning to understand. Some binary stars don't just evolve, they shapeshift, altering their very identity in cosmic sleight of hand that baffles astronomers. Meet HD 142527, a binary system where the smaller companion star is a celestial chameleon, its spectrum shifting so dramatically and unpredictably that it can impersonate a red giant, a white dwarf, or even a newborn protostar, sometimes cycling through multiple disguises in a single orbit. This stellar masquerade begins with the system's extreme environment. The primary star, a massive young giant, is surrounded by a sprawling disk of gas and dust, material it voraciously consumes while flinging excess outward in violent winds. The smaller companion orbits deep within this chaos, plowing through dense pockets of debris that alternately cloak and reveal its true nature. When shrouded in thick carbon monoxide clouds, the star's light filters through molecules that absorb specific wavelengths, making it appear cooler and redder. Moments later, as it punches through a clearing, ultraviolet radiation from the primary star ionizes its atmosphere, transforming its spectral signature into something hotter and bluer. But the real enigma lies in the speed of these changes. Most variable stars shift over days or weeks. HD 142527 companion can flip its entire spectral identity in hours. One evening, telescopes might classify it as a modest K-type star. By dawn, its spectrum could resemble a searing O-type giant. These aren't subtle variations, they're wholesale reinventions, as if the star is trying on costumes with cosmic glee. The key to this illusion: the companion star isn't just passively reflecting its environment, it's actively reshaping it. As it plows through the disk, its gravity creates shock waves that heat surrounding gas to thousands of degrees, producing temporary emission lines that masquerade as exotic elements. Meanwhile, material ripped from the disk swirls into a transient atmosphere around the star, a churning veil that filters its light unpredictably. At times, this stolen cloak grows so thick it triggers false hydrogen absorption features, tricks that once fooled astronomers into believing they discovered a water-rich super-Earth orbiting the star. What makes this system revolutionary isn't just the star's deception, it's the challenge it poses to classification itself. Modern astronomy relies heavily on spectral typing to determine a star's age, composition, and distance. HD 142527 companion exposes the fragility of those assumptions, proving that environment can rewrite a star's apparent identity as easily as smoke and mirrors alter a magician's act. The implications stretch beyond this one system. If stars can disguise themselves so thoroughly, how many other cosmic imposters lurk in our catalogues? Could dead white dwarfs hiding in debris disks be masking as main sequence stars? Might some young protostars actually be elderly stars in disguise? The universe, it seems, enjoys a good costume party, and HD 142527 is its most enigmatic guest. In the binary system VFTS 102, astronomers discovered a star that defies all expectations, spinning so fast it's literally tearing itself apart at the seams. Clocking in at an astonishing 1 million miles per hour, 100 times faster than our sun's rotation, this stellar speedster completes a full rotation in less than 25 minutes. At that velocity, its equator bulges outward violently, stretching the star into an oblate shape so extreme it's barely held together by gravity, the culprit behind this cosmic centrifuge. A companion star whose gravitational meddling likely kicked this star's rotation into overdrive, turning it into one of the fastest spinning objects in the known universe. The physics behind this breakneck spin reads like a stellar crime scene. The primary star, a massive blue giant, likely formed with a typical rotation speed. But when its smaller companion reached the end of its life and collapsed into a compact neutron star, the transfer of angular momentum during the death throes sent the surviving star whirling like a figure skater pulling in their arms. As the system's total spin had to be conserved, the neutron star's contraction forced the remaining star to compensate by spinning faster, much faster. Now the blue giant's centrifugal forces are so intense, they've flung nearly 10% of its mass into space, creating a glowing equatorial disk of ejected material that orbits the star like a cosmic hula hoop. What makes VFTS 102 even more extraordinary are the side effects of its ludicrous speed. The star's rapid rotation has generated monstrous magnetic fields billions of times stronger than Earth's, that channel particles into jets streaming from its poles at nearly the speed of light. These jets, visible in X-ray and radio wavelengths, spiral outward in corkscrew patterns due to the star's dizzying spin, creating helix-shaped trails of plasma that stretch light years into space. Meanwhile, the star's surface temperature varies wildly from equator to poles, a difference of over 10,000 degrees, because the bulging midsection is stretched so thin. It cools significantly compared to the compact polar regions. But the most terrifying consequence might be its inevitable fate. Stars spinning this fast flirt dangerously with a breakup limit, the velocity at which centrifugal force overpowers gravity. If VFTS 102 accelerates further, it could literally fling itself apart in a cataclysmic explosion, scattering its remains across the cosmos in a glittering nova-like event. Alternatively, its rotation might gradually slow as it sheds mass, eventually settling into a less extreme but still bizarre state. Either way, this system stands as a testament to gravity's ability to rewrite a star's destiny, not just through destruction, but through transformation, turning an ordinary sun into a cosmic whirligig spinning on the edge of oblivion. Most planets would crumble under the gravitational chaos of a binary star system, but not Kepler 453b. This gas giant, roughly 60% larger than Jupiter, orbits twin suns in the constellation Lyra, surviving where most worlds would be torn apart. The stars it calls home couldn't be more different, one a yellow dwarf similar to our Sun, the other a smaller, cooler orange dwarf. Their contrasting masses create a gravitational tug of war, yanking the planet's orbit into an elongated ellipse that sends it weaving between them like a cosmic pendulum. What makes this planet extraordinary isn't just its resilience, it's the sheer improbability of its existence. Binary stars typically disrupt planet formation, their competing gravity scattering protoplanetary material before it can coalesce. Yet Kepler 453b's orbit remains stable, locked in a delicate resonance where the star's pulls counteract each other just enough to prevent catastrophe. The secret lies in its distance far enough that the star's gravity averages out into a predictable rhythm, yet close enough to bask in the glow of two suns. From the planet's hypothetical moons, the sky would be a mesmerizing light show. Double sunrises casting ever-shifting shadows, eclipses where one star creeps across the other, and nights that never grow truly dark. But survival comes at a price. The planet's elliptical path subjects it to extreme temperature swings, with seasons that fluctuate wildly as it loops closer to one star than the other. Atmospheric models suggest relentless storms churn across its surface, driven by the uneven heating, a world where hurricanes might span continents and last for centuries. Even its rotation is likely chaotic, tidally locked to neither star but torqued by their alternating tugs, leaving its axis wobbling unpredictably over millennia. The real revelation, Kepler 453b might not be alone. Recent simulations suggest its orbit creates gravitational, safe zones, where smaller, rocky planets could theoretically exist pockets of stability in the system's turbulent sea. If confirmed, it would prove that even in the most chaotic binaries, the universe finds ways to carve out havens for worlds. For astronomers, this system is more than a curiosity. It's a blueprint for how planets can endure where the rules say they shouldn't, rewriting our understanding of where life might take root in the cosmos. Some stars don't burn steadily, they flicker like candles caught in a cosmic draft. In the binary system VV Coronii Borealis, the larger star pulses with such erratic brilliance, its light curves resemble a seismograph during an earthquake. One day it might dim by 20%, the next it could flare unpredictably before plunging back into darkness. These aren't the orderly pulsations of typical variable stars, they're violent, chaotic surges that defy every model of stellar behavior. The culprit lies in the star's turbulent relationship with its companion, a white dwarf orbiting perilously close. Every few decades, the dwarf's gravity disrupts the larger star's outer layers, triggering spasms of mass loss that shroud the system in thick clouds of carbon-rich dust. When these clouds drift across our line of sight, the star's light flickers as if someone is toggling a dimmer switch, but the real mystery is the speed of these changes. Most dust-obscured variables fade gradually over months. VV Coronii Borealis can plunge into obscurity in days, then snap back to full brightness just as fast. Spectroscopic sleuthing reveals even stranger details. The carbon dust isn't spreading evenly, it's clumping into fractal-like tendrils, some so dense they block 99% of the star's light. Infrared observations show these tendrils are warmer than expected, suggesting the companion white dwarf is heating them with ultraviolet radiation, baking the dust into peculiar molecular structures. At times, the entire system vanishes from optical telescopes entirely, only to reappear in infrared as a blazing thermal ember. What makes this flickering star so revolutionary isn't just the unpredictability, it's the challenge it poses to stellar physics. Conventional models assume dust forms in smooth, expanding shells around aging stars. VV Coronii Borealis shreds that assumption, proving dust can erupt in chaotic, asymmetric plumes like smoke billowing from a wildfire. The system's wild light swings also hint at hidden instabilities in the primary star's core, where nuclear fusion might be sputtering unevenly like an engine misfiring. The most tantalizing clue, the flickering is accelerating. A century ago, the star's dimming episodes occurred every few decades. Now they happen every 5 to 10 years, as if some internal timer is winding up toward an unknown climax. Some theorists speculate the white dwarf is spiraling inward, its gravitational pokes growing more frequent and disruptive. If so, the flickering might be a prelude to something far more dramatic, a catastrophic merger or nova explosion that could rewrite the system's fate overnight. For now, VV Coronii Borealis keeps its secrets, its light dancing to a rhythm only it understands. Every unpredictable flicker carries a message, a reminder that even the most familiar cosmic phenomena can still surprise us when we look closely enough. In the tumultuous binary system GG Carinii, two massive stars wage an endless battle over a shared prize, a swirling disk of gas caught between them, stretched thin by their competing gravity. These aren't just stars orbiting each other, they're celestial gladiators yanking matter back and forth in a cosmic tug of war so fierce, it triggers violent outbursts visible across the galaxy. The primary star, a blue supergiant 30 times the mass of our Sun, should dominate its smaller companion. But the underdog, a Wolf-Rayet star, dense and searing hot, fights back with a stellar wind so powerful it blasts through the disk like a hurricane, carving gaps and launching shockwaves that ripple through the system. The real spectacle unfolds when the disk's equilibrium breaks. Gas stolen by one star often spirals inward too fast, overloading its surface until the accumulated energy detonates in unpredictable flares. In 2012, astronomers caught GG Carinii in the act, a month-long eruption where the system's brightness surged tenfold, spewing ultraviolet radiation and high-speed jets in opposite directions. The outburst wasn't caused by either star alone, but by their combined greed. The disk, torn asymmetrically by their competing pulls, funneled too much material at once into unstable orbits. It's like two children pulling on a rope until it snaps, sending both tumbling. What makes this struggle so fascinating is the aftermath. Instead of calming down, the stars reshape the debris into new battle lines. The Wolf-Rayet's fierce winds sweep up ejected material, molding it into spiral arms that stretch halfway to its rival. Meanwhile, the supergiant retaliates by channeling its own outflow into a narrow, focused beam, a celestial blowtorch aimed straight at the disk's weakened regions. The resulting chaos defies simple classification. Sometimes the system resembles a pulsar with jets, other times a protoplanetary disk gone rogue. The stakes are higher than just stellar drama. GG Carinii's fireworks provide a rare glimpse into how massive binaries forge elements. The shockwaves from their clashes fuse atoms into heavy metals like gold and platinum, scattering them into space through their winds. Every outburst seeds the surrounding nebula with stardust that might one day form planets or even life. Yet the most unsettling revelation is how fleeting these duels are. Simulations suggest the star's orbits are decaying, their dance growing tighter and more volatile with each passing millennium. One day, their tug of war will end in catastrophe, either a merger that spawns a single hypergiant or a supernova that obliterates the disk entirely. Until then, Gigi Carani remains a live laboratory for the universe's most extreme gravitational feuds, proving that even among stars, sharing isn't always peaceful. Sometimes it's a fight to the finish. In the constellation Cetus, astronomers stumbled upon a celestial paradox, a binary system where one star refuses to follow the universe's temperature laws. Known as HD 209458, this pair consists of a seemingly ordinary sun-like star and a companion that baffles every textbook definition of stellar behavior. The rogue star's spectral class, a categorization based on the light it emits, suggests it should burn at around 6,000 degrees Celsius, similar to our Sun. Yet direct measurements reveal a surface temperature nearly twice that scorching hot, as if the star forgot to read its own owner's manual. The mystery deepens when you examine the star's light output. Its spectrum shows absorption lines typical of a cooler star, with traces of iron and titanium, but its ultraviolet emission screams with the energy of a far hotter object. It's like finding a candle that flickers with the heat of a blowtorch. The contradiction has astronomers questioning whether our tools for measuring stellar temperatures are flawed, or if this star is playing by its own rules. The likely culprit, the star's turbulent relationship with its binary partner. Locked in a tight orbit, the two stars exchange material through a chaotic stream of superheated gas. As the cooler star siphons matter from its companion, the stolen plasma doesn't settle evenly. It slams into the star's surface at supersonic speeds, creating localized hotspots that glow far hotter than the surrounding areas. These patches, some spanning thousands of miles, skew the star's overall temperature readings upward like blisters on an otherwise cool skin. But the real enigma is why these hotspots don't dissipate. Normally, stellar convection would redistribute the heat, smoothing out temperature extremes. Yet this star's magnetic field, oddly concentrated in looping arcs, acts like a cage, trapping the scorching material in place. The result is a cosmic patchwork, a surface riddled with searing islands amid a cooler sea, defying the uniform temperatures seen in most stars. The implications rattle the foundations of stellar astrophysics. If stars can masquerade as one spectral type while hiding another, how many other misclassified stars lurk in our catalogues? Could this explain why some stars appear older or younger than their surroundings? HD 209458 forces us to reconsider whether temperature and spectral class are as inseparable as we once thought, or if the universe, as always, enjoys throwing us a curveball when we least expect it. Perhaps the most tantalizing clue lies in the star's flickering X-ray emissions, which spike unpredictably. These bursts, possibly tied to magnetic reconnection events, suggest the star isn't just broken, it's reinventing how stars behave under extreme binary stress. For now, it stands as a cosmic rebel, a reminder that the universe's rulebook always has room for footnotes, and that some stars would rather burn than fade into conformity. Some stars don't just age, they carry scars from cosmic crimes long past. In the binary system NGC 5839, astronomers found a pair of stars with a history written in violence, their orbits and compositions screaming of a cataclysm that should have torn them apart. The larger star, a blue straggler, burns unnaturally hot and young, its outer layers laced with elements that shouldn't exist in a star of its size, the smaller companion. A neutron star, silent and brooding, spinning lazily as if exhausted from some ancient battle. Together, they form a celestial cold case, a system where the evidence points to a third star that vanished without a trace, consumed in a gravitational ambush millions of years ago. The smoking gun lies in their motion. Unlike most binaries which orbit in tidy ellipses, these two whirl around each other in a lopsided, almost drunken path. Simulations tracing their movements backward reveal an explosive past. Their current orbits only make sense if a massive third star once anchored the system, its sudden destruction sending the survivors careening into their current unstable dance. The neutron star's slow spin supports this. It's not the rapid-fire rotation typical of pulsars, but a sluggish turn, as if it formed not from a supernova's clean collapse, but from a chaotic merger or collision that robbed it of spin. Then there's the blue straggler's unnatural youth. Stars this massive should burn out quickly, yet it shines with the vigor of a newborn. Spectroscopic analysis reveals why. Its outer layers are polluted with carbon, nitrogen, and heavy metals debris that likely came from the demolished third star. The leading theory, a violent game of gravitational pinball where the original trio destabilized, causing two stars to collide and merge, while the third was flung away or shredded into a disk of debris. The resulting explosion wouldn't have been a standard supernova, more like a stellar demolition, scattering wreckage that the surviving blue straggler later scooped up, rejuvenating itself with stolen fuel. The most haunting clue, though, is the neutron star's silence. Most stellar corpses of its kind emit radio pulses or X-rays, but this one is eerily quiet. Some researchers speculate its magnetic field was scrambled in the catastrophe, leaving it dormant, a dud remnant of whatever apocalyptic event reshaped the system. Others suggest it's cloaked in a shroud of dust, the last fragments of its victims still circling like a ghostly veil. What makes NGC 5839 so unsettling isn't just its history, it's the implication that such events might be common. For every orderly binary, there could be dozens of these cosmic survivors, their scars hidden beneath layers of time and distance. They remind us that the universe doesn't just create stars, it forges them in chaos, and sometimes the only witnesses left are the ones that got away. Deep in the Milky Way, two stars perform a synchronized light show so precise, it's as if the universe itself composed their rhythm. The binary system KIC 9163796 isn't just pulsing, it's harmonizing, its star's brightness fluctuations locking into perfect sync over time like celestial metronomes tuning to the same invisible conductor. The primary star, a yellow giant, throbs with slow, deep surges of light every 13 days, while its smaller companion, a hot subdwarf, flickers rapidly every 46 minutes. Yet despite their drastically different rhythms, something extraordinary happens as they orbit. Their pulsations begin to mirror each other, the smaller star's rapid beats gradually aligning with its partner's slower cadence until they pulse in unison. This cosmic synchrony isn't just poetic, it's a gravitational revelation. The stars' connection runs deeper than their shared orbit. Their interiors are literally speaking to one another through seismic waves that ripple across the gulf between them. Every time the primary star swells outward, its gravity tugs on the subdwarf's core, amplifying specific vibrational modes in its structure. In return, the subdwarf's pulsations send shockwaves through the shared magnetic field linking the pair, which rebound into the giant's outer layers like echoes in a canyon. Over centuries, this feedback loop has tuned their oscillations into harmony, a phenomenon called tidal resonance that's more commonly seen in planetary moons than stars. What makes this system revolutionary is how the synchronization unveils hidden forces. Normally, stellar pulsations are driven by internal processes, heat convection, nuclear reactions, or magnetic fields. But in KIC 9163796, the dominant force shaping the pulsations isn't coming from inside either star, it's the gravitational dialogue between them. By analyzing the subtle delays in their mirrored pulses, astronomers have mapped the stars' tidal interactions with unprecedented precision, revealing how the pull of one star distorts the other's shape, right down to how much its equator bulges during close approaches. The implications stretch far beyond this odd couple. If tidal resonance can override a star's natural pulsations, it suggests binary interactions might explain anomalies in other variable stars. Those erratic flickers previously blamed on internal turbulence could instead be whispers from unseen companions. The discovery also hints at a universal truth. Stars in close partnerships don't just orbit each other, they reshape each other's very essence, turning solitary rhythms into a shared song. Yet the most haunting beauty lies in the system's imperfections. The synchronization isn't flawless. Every few orbits, the subdwarf's pulses lag slightly behind, as if resisting the giant's pull before surrendering again to harmony. These hiccups, far from flaws, are treasures. Each one encodes information about the star's internal structures, like seismic waves revealing Earth's layers after an earthquake. By decoding these glitches, astronomers have pieced together the subdwarf's bizarre composition. A helium-rich core wrapped in a paper-thin hydrogen shell, a relic of some violent interaction in the system's past. For now, KIC 9163796 keeps perfecting its duet, a living testament to gravity's power to orchestrate order from chaos. Its pulsing light carries a message that even across the void, no star truly dances alone. Deep in the constellation Cygnus, a star swings through space like a wrecking ball on a cosmic chain, its orbit so erratic, it defies every law of orderly motion. This rebel star, part of the binary system KIC 8462852, doesn't follow the smooth, predictable ellipses of most celestial pairs. Instead, it lurches along a path that zigzags wildly, accelerating and decelerating as if tugged by invisible hands. For decades, astronomers dismissed the anomalies as glitches until precise measurements revealed the truth. Something unseen is yanking this star off course, rewriting its trajectory with every pass. The star's dance is a masterclass in celestial chaos. Normally, binary orbits stabilize over time, settling into rhythmic loops as gravity smooths out irregularities. But KIC 8462852's primary star surges ahead at odd intervals, sometimes racing close to its companion, other times hanging back as if hesitant. The deviations aren't random, they follow a distinct pattern, peaking every few years like clockwork. The best explanation, a hidden third object, likely a rogue planet or low-mass brown dwarf, lurking in the system's outer darkness. Its gravity tugs the star subtly but persistently, like a child wobbling a spinning top with occasional, well-timed nudges. What makes this cosmic pendulum so mesmerizing isn't just the disruption, it's the precision of the havoc. The perturbing object's influence suggests an orbit tilted sharply relative to the binary pair, its pulls strongest at specific points in its long, looping path. Simulations show the intruder's gravity creates kinks in the star's motion, warping its orbit into a shape resembling a tangled slinky rather than a neat ellipse. Yet despite the chaos, the system persists, its stars locked in a grudging embrace even as their unseen tormentor reshapes their dance. The implications ripple far beyond this one system. If such shadowy influences are common, they could explain anomalies in other binaries, mysterious eclipses that arrive late, stars that speed up inexplicably, or pairs that drift apart when physics says they should converge. Some astronomers speculate these hidden objects might be remnants of the system's birth, planets flung outward during early gravitational tussles but never fully ejected. Others propose darker possibilities, primordial black holes drifting undetected between stars, their presence betrayed only by the tremors they send through their hosts' orbits. Yet the true wonder lies in the resilience of the binary itself. Against all odds, the stars endure, their bond flexing but never breaking under the strain. It's a reminder that even in the cosmos, relationships aren't always tidy sometimes. They're messy, unpredictable, and all the more fascinating for it. And somewhere in the darkness, the pendulum keeps swinging, its unseen conductor still pulling the strings. Imagine a star wrapped in a cosmic veil so thick, not even its own light can escape, a celestial phantom so well hidden, astronomers spent decades convinced it was alone. In the binary system Ogle LMCCP 0227, the primary star appears to float in eerie solitude, its spectral lines betraying no hint of a companion. Yet something unseen tugs at it, warping its orbit with silent persistence. The truth is stranger than fiction. This star isn't alone. It's locked in a gravitational embrace with a partner completely cloaked by a swirling shroud of gas, a nebula-like envelope so dense it swallows nearly all traces of the star within. This gaseous veil isn't just hiding the companion, it's rewriting it. The obscured star, likely a hot blue giant, burns fiercely beneath its opaque blanket, its ultraviolet radiation ionizing the surrounding hydrogen into a glowing, ruby-red halo. From Earth, telescopes catch only fleeting glimpses of the trapped star's light, faint flickers that pierce the fog when turbulence in the gas momentarily parts the curtain. These rare windows reveal a nightmare environment. Temperatures inside the veil soar to tens of thousands of degrees, with pressure waves from the star's radiation driving supersonic winds that shred the gas into fractal-like tendrils. The result, a celestial matryoshka doll, a star within a storm, its fury muffled by the very material it's trying to blast away. What makes this system revolutionary isn't just the veil's opacity, it's the way it defies stellar life cycles. Gas clouds this dense typically dissipate within millennia, blown clear by their star's fierce winds. Yet here, the veil persists, replenished by a sinister symbiosis. The primary star, a pulsating yellow supergiant, sheds material in slow, massive waves, ejections so vast they drip like cosmic molasses into the companion's gravitational well. As the gas spirals inward, the blue star's radiation cooks it into complex molecules, creating a self-sustaining cycle where the veil feeds on its own destruction. The most haunting detail, the veil isn't static. Observations spanning 20 years show its structure morphing unpredictably, sometimes contracting into a tight cocoon, other times flaring outward in jagged plumes. These shifts hint at titanic battles beneath the surface, where the trapped star's magnetic fields wrestle control of the gas from its partner's gravity. During one remarkable event in 2014, a chunk of the veil the size of our solar system tore free entirely, momentarily exposing the companion's scorching face before fresh material rushed in to seal the breach. For astronomers, this system is more than a curiosity, it's a cosmic laboratory. The veil's chemistry, rich in carbon chains and organic molecules, mimics conditions thought to exist in the early universe where the first stars ignited inside similar shrouds. Its persistence challenges models of how binary systems evolve, proving that some stars don't just live together, they smother one another, their fates tangled in a dance of light and shadow. And somewhere beneath that swirling crimson fog, a star fights to be seen. Its struggle etching whispers across the spectrum, a reminder that even in the vastness of space, some secrets refuse to stay hidden forever. Some cosmic partnerships shouldn't last, yet they do, defying every law we thought governed stellar motion. Meet Kick 10,544,976, a binary system where one star is a lightweight red dwarf, barely a tenth the mass of our Sun, and the other is a monstrous white dwarf, packing the Sun's mass into an Earth-sized sphere. According to physics, this lopsided pairing should be unstable. The white dwarf's gravity ought to either fling its tiny companion into space or devour it whole. Yet here they are, locked in a perfectly synchronized orbit, circling each other every 3 days like mismatched dancers, somehow keeping perfect time. The mystery lies in their mass ratio. Most stable binaries involve stars of roughly similar sizes, their gravitational pulls balanced like equally matched boxers in a ring. But in KIC 10,544,976, the white dwarf outweighs its partner by a factor of 10, a disparity so extreme their orbits should decay within millennia. The fact that they've persisted for billions of years suggests something extraordinary is at play. Either a hidden force stabilizing their dance or a violent past that left them improbably intertwined. One clue comes from the white dwarf's composition. Spectroscopic analysis reveals traces of heavy elements like oxygen and neon on its surface debris that shouldn't exist unless it once cannibalized a third star. Theorists propose a dramatic backstory. This system may have begun as a trio with two red dwarfs orbiting a larger star. When the primary star collapsed into a white dwarf, its death throes ejected enough material to destabilize the trio, sending one red dwarf hurtling into space while the survivor settled into this bizarrely stable orbit. The ejected mass could have acted like a gravitational anchor, sapping energy from the system and leaving the remaining pair in an unnaturally tight embrace. Another possibility is magnetic magic. Red dwarfs are notorious for their powerful magnetic fields, which can interact with a white dwarf's own magnetism in ways we don't fully understand. If the star's fields are aligned just right, they might create an invisible scaffold, reinforcing their orbit against collapse. Observations show erratic flares in the system, sudden bursts of energy that hint at magnetic reconnection events where field lines snap and rewire, releasing enough force to nudge the stars back into equilibrium. Yet the most tantalizing explanation challenges our understanding of gravity itself. Some models suggest that in extreme binaries like this, tidal forces, the same pulls that make Earth's oceans rise and fall could be subtly reshaping the stars' interiors, redistributing mass in ways that stabilize their motion. The red dwarf might be stretching ever so slightly toward its heavyweight partner, its distorted shape acting like a counterweight, subtly balancing the system like a spinning top weighted just right. Whatever the reason, KIC 10,544,976 stands as a cosmic contradiction. A binary that shouldn't exist, yet shines defiantly against the void. Its persistence forces us to reconsider the rules we thought were absolute, proving that even in the ordered dance of the cosmos, some partners move to a rhythm only they can hear. Deep in the constellation Perseus, a star pulses with a rhythm so precise, it seems to breathe, expanding and contracting over years like a giant cosmic lung. This isn't just a flickering variable star, it's one half of the binary system Rs Persei, where the primary star swells and shrinks in a slow, hypnotic cycle, its radius oscillating by millions of miles with mechanical regularity. The cause, a delicate balancing act between gravity and radiation, where the star's outer layers teeter on the edge of stability, perpetually falling inward only to be pushed back out by the fury of nuclear fusion beneath. What sets this star apart is the sheer scale of its transformations. Over a 5-year cycle, its diameter balloons by nearly 20%, enough to swallow the orbit of Venus if placed in our solar system, before collapsing back to its original size. Unlike typical pulsating stars whose brightness changes dominate their behavior, Rs Persei's luminosity barely flickers. The real drama unfolds in its structure, where entire atmospheric layers rise and fall like tides, driven by pressure waves resonating through its helium-rich core. Imagine a bellows forged from stellar plasma, inhaling and exhaling on a timescale that dwarfs human lifetimes. The secret to this rhythmic dance lies in the star's partnership with its companion, a blue supergiant orbiting just close enough to stir the pot. Every periastron, their closest approach, the blue star's gravity tugs on the pulsating giant's outer layers, amplifying its natural oscillations. Spectroscopic studies reveal how these tidal nudges synchronize with the star's internal pressure waves, creating a feedback loop where each expansion primes the next contraction. It's as if the companion star is conducting an orchestra, its gravitational baton cueing the crescendos and decrescendos of its partner's breath. Yet the most mesmerizing detail is how this cosmic respiration shapes the system's environment. As the star expands, it sheds material in slow, rippling waves, forming concentric shells of dust that glow in infrared. When it contracts, these shells fracture under the sudden release of radiation, creating luminous shock fronts that spiral outward like interstellar tsunamis. The companion star, meanwhile, plows through this ever-changing landscape, its fierce stellar wind carving tunnels and cavities in the ejected material structures that twist and warp with each new breath of the primary. Astronomers study Rs Persei not just for its beauty, but for the secrets it holds about stellar aging. The star's pulsations act like a natural ultrasound, revealing conditions in its core where helium fuses into carbon, a process normally hidden beneath opaque outer layers. By tracking how the rhythm speeds up or slows down over decades, scientists can infer changes in its internal composition, watching in real time as a star inches toward its eventual fate as a supernova. But perhaps the most profound lesson here is one of cosmic interconnectedness. This star doesn't pulse in isolation. Its rhythm is choreographed by the gravitational whispers of its partner, a reminder that even the mightiest celestial bodies are shaped by the company they keep. In the grand ballet of the universe, even breathing is a shared act. Some binary stars don't just orbit, they reflect, turning their shared space into a hall of mirrors where light bends into illusions so convincing they trick even the most advanced telescopes. In the system V921 Scorpii, two massive stars circle each other so closely, their surfaces act like colossal funhouse mirrors, warping and amplifying each other's light in ways that make single stars appear as twins or vanish entirely behind curtains of refracted brilliance. Here's how the illusion works. The primary star, a blue supergiant, burns hot enough to bathe its companion in intense ultraviolet radiation. But when the cooler secondary star, a yellow giant, passes behind it, something extraordinary happens. Instead of just eclipsing the blue star's light, the yellow star's thick atmosphere refracts it, bending rays around its edges like light through a prism. From Earth's vantage point, this creates ghostly duplicate images of the blue star, flickering mirages that appear slightly offset from the original. During peak distortion, up to 4 phantom stars materialize in a cross-shaped pattern around the yellow giant, each a time-delayed echo of the primary star's light taking a different path through the gravitational lens of its partner. The illusions don't stop there. When the blue star passes in front, its fierce radiation ionizes the yellow star's outer layers, creating a temporary shell of plasma that acts like a funhouse mirror. Light from the yellow giant bounces off this shell at odd angles, sometimes converging into a bright hotspot on the blue star's surface that shouldn't exist, a virtual image so convincing early astronomers mistook it for a physical feature. Other times, the refracted light smears the yellow star's image into a crescent or ring, an effect normally seen in distant galaxies gravitationally lensed by galaxy clusters, not in something as small as a binary system. What makes V921 Scorpii truly bizarre is how these illusions warp over time. Unlike static optical effects, these reflections pulse and twist as the star's atmospheres churn. The yellow star's turbulent winds create pockets of varying density, turning its refractive lens into a dynamic kaleidoscope. One moment, the blue star's duplicates might sharpen into perfect replicas. The next, they dissolve into shimmering streaks like reflections in a pond disturbed by a thrown stone. The most haunting trick, sometimes the entire system disappears. When both stars align perfectly with Earth, the blue star's light bends so severely around the yellow star's limb that it cancels itself out through destructive interference, a phenomenon called Einstein's eclipse. For up to 12 minutes, the binary fades to near invisibility, as if someone flipped a cosmic light switch. These illusions aren't just celestial sleight of hand, they're tools. By studying how the mirages shift, astronomers map the star's atmospheric structures with precision impossible by other means. The distortions reveal the yellow star's hidden weather patterns, supersonic jet streams, storm fronts large enough to engulf Jupiter, and even magnetic loops that channel light like fiber optic cables. Yet the greatest lesson might be humility. If a simple binary can conjure such convincing phantoms, how many other cosmic facts are just tricks of the light? V921 Scorpii reminds us that in the universe, seeing isn't always believing sometimes. It's the first step into the funhouse. Among the cosmos' most baffling stellar oddities is HS 2231 plus 2441, a binary system where one star defies classification by behaving as two entirely different stars at once, a cosmic doctor. Jekyll and Mr. Hyde. The primary star, a pulsating hot subdwarf, emits a blistering blue-white glow typical of its compact helium-burning kind. Yet when astronomers analyzed its spectrum, they found the impossible signatures of a second star type, those of a cool, bloated red giant superimposed on the same object. It wasn't a twin or a companion. The same star was somehow exhibiting both identities simultaneously, flickering between them like a celestial shape-shifter. The key to this duality lies in the star's turbulent relationship with its partner, a neutron star locked in a punishingly close orbit. Every few days, as the binary swings through its closest approach, the neutron star's gravity peels away layers of the subdwarf's outer atmosphere, exposing deeper, cooler regions normally hidden beneath its searing surface. But here's the twist: the stolen material doesn't just vanish. It forms a vast, tenuous shroud around the system, a halo of gas so thick it mimics the extended atmosphere of a red giant. When viewed edge-on, telescopes catch light filtering through both the subdwarf's bare core and this phantom envelope, creating the illusion of a hybrid star that shouldn't exist. Even stranger, the star's behavior flips depending on which face it shows. During phases where the subdwarf dominates, it pulses with a regular rhythm, its helium-rich core contracting and expanding like a heartbeat. But when the red giant's spectral lines strengthen, these pulsations vanish, as if the star forgets its true nature while cloaked in its cooler alter ego. The transitions aren't smooth, they happen in abrupt jumps like a dial switching between channels. What makes this masquerade more than just a trick of the light is the star's impact on its environment. The neutron companion, feeding on the subdwarf's stripped gas, fires off X-ray bursts that vary wildly depending on which stellar personality is donating material. Cooler, red giant-like ejections produce softer X-rays, while direct siphoning from the subdwarf's core triggers violent high-energy flares. The system's accretion disk, normally a steady structure, flickers between states, sometimes smooth and laminar, other times fracturing into clumps and spirals as if unsure which star it's serving. The implications rewrite stellar playbooks. If stars can project multiple identities based on their binary interactions, how many other misclassified objects hide in plain sight? Could some variable stars actually be stable stars with unstable partners, their shifting spectra reflecting external chaos rather than internal change? HS 2231 plus 2441 forces astronomers to reconsider the very language they use to categorize stars, because in the universe's wildest neighborhoods, sometimes a star isn't just one thing. It's whatever survival demands it to be. Deep in the constellation Scorpius lies a cosmic riddle wrapped in a stellar enigma. The binary system GROJ 165540, where one star harbors a silent monster in its core. At first glance, this system appears ordinary, a blue supergiant orbiting an unseen companion, but the beast lurking beneath the surface is anything but ordinary. The primary star's light flickers erratically, its spectrum tinged with strange absorption lines, as if something beneath its surface is warping its very essence. The truth, that seemingly normal star is being hollowed out from within, its core replaced by a neutron star that fell into its heart like a cosmic parasite. This stellar horror story began billions of years ago when the neutron star itself, the remnant of a supernova, drifted too close to its now ensnared partner. Instead of orbiting safely outside, it plunged straight into the supergiant's outer layers, sinking through the star's diffuse envelope like a bullet through fog. Normally, such an intrusion would tear a star apart, but this neutron star was dense enough to survive the journey, slipping past the outer gases until it settled near the core. Now it orbits inside the star, a hidden dynamo churning the surrounding plasma into violent turbulence. The effects are catastrophic. The neutron star's gravity churns the supergiant's innards, disrupting nuclear fusion and creating bizarre convective currents that make the star's surface pulse unpredictably. Every few years, the system erupts in X-ray flares, not from outside accretion, but from material the neutron star scrapes directly from its host's core, like a bear raiding a beehive from within. The stolen matter spirals down magnetic field lines, igniting thermonuclear detonations that ripple outward, making the entire star shudder. Yet the most unsettling discovery came from spectral analysis. The star's outer layers contain absurdly high concentrations of rare earth elements like europium and samarium metals normally forged only in supernova or neutron star collisions. The likely source, the neutron star's surface, eroded over millennia by the supergiant's internal currents, sprinkling its exotic crust into the star's atmosphere like poison in a well. This stellar cannibal is being force-fed its own murderer's remains. What makes this system revolutionary isn't just its violence, it's the glimpse it offers into stellar evolution's darkest corners. Most models assume binary stars interact externally, but GROJ 165540 proves stars can consume and remodel each other from within. If such embedded binaries are common, they might explain other cosmic anomalies, stars with unexplained heavy elements, erratic pulsations, or even zombie stars that keep burning long after their fuel should be exhausted. The neutron star's fate is the ultimate cosmic irony. Though it devours its host today, the supergiant will one day collapse in a supernova, an explosion that could either fling the neutron star free like a bullet from a gun or merge them into something even stranger, a black hole wrapped in the shredded skin of its victim. Until then, this binary remains a ticking time bomb, its hidden heart beating to a rhythm only destruction understands. In the constellation Lyra, astronomers discovered a cosmic paradox that rewrites the rules of time itself. The binary system HD 140283, where one star gleams with the brilliance of youthful vigor while its partner flickers like a relic from the dawn of creation. The primary star, a blue straggler, burns unnaturally hot for its age, its surface temperatures rivaling those of newborn stars. But its companion is the true enigma, a subgiant so ancient its iron content is nearly non-existent. Spectroscopic analysis dates this star to an impossible 14.5 billion years older than the universe's estimated 13.8 billion years. It's like finding a grandfather clock ticking in a world before time began. This cosmic contradiction starts with the subgiant's composition, or rather, its lack thereof. The star contains less iron than any other known object in the Milky Way, a telltale sign it formed before supernova seeded the cosmos with heavy elements. Its light carries the spectral fingerprints of primordial hydrogen and helium, virtually untouched by the chemical enrichment that defines younger stars. Yet here it orbits alongside a star that behaves like a celestial teenager, glowing with the intensity of something born in a later, more metal-rich era. The pairing shouldn't exist. Stars this old were thought to have died eons ago, and blue stragglers require fresh fuel from binary interactions to maintain their unnatural youth. The secret might lie in an ancient theft. The blue straggler likely siphoned hydrogen from its elderly companion, rejuvenating itself like a vampire draining a victim's vitality. But here's the twist. The subgiant's extreme age suggests it wasn't just a donor. It might be a refugee from an earlier universe. Some theorists propose it originated in a population 3-star cluster, the very first generation of stars born from pure hydrogen and helium after the Big Bang. These primordial giants were thought to have burned out within millions of years, their supernova scattering the elements that built later stars. Yet this one survived, hidden in a quiet corner of the galaxy until its encounter with the blue straggler locked it into this bizarre partnership. The implications ripple beyond stellar oddities. If HD 140,283 subgiant truly predates the cosmos' estimated age, it could mean our measurements of universal expansion are incomplete, or that pockets of the universe formed earlier than we thought. Alternatively, the star might have been born in a region so isolated it avoided the chemical pollution of later supernova, preserving its prehistoric purity by cosmic accident. Either scenario forces astronomers to confront gaps in our understanding of time's arrow. Yet the most haunting question remains: what other chronological paradoxes hide in plain sight? If one star can defy time's boundaries, others might too, whispering secrets about epochs we've only begun to imagine. For now, HD 140,283 stands as a cosmic hourglass where sand flows both ways, challenging us to reconsider when the story of the universe truly began. From vampire stars stealing their partner's lifeblood to black widow pulsars blasting their companions into oblivion, we've journeyed through 50 of the universe's most bizarre binary systems, each one defying expectations and rewriting the rules of astrophysics. These cosmic oddities aren't just curiosities, they're laboratories where gravity, magnetism, and sheer chaos collide in ways we're only beginning to understand. Think about the zombie stars that cheat death, the shape-shifting pulsars that vanish and reappear, or the stellar chameleons that oscillate between identities like celestial actors. These systems force us to question everything we thought we knew about how stars live, die, and interact. Consider the implications. If a single star can be stretched into a teardrop by tidal forces, or a black hole can hide undetected in a binary's gravitational sway, what else have we overlooked? The universe thrives on extremes, and binary systems are its most unrelenting teachers. They've shown us that planets can form in the crossfire of twin suns, that supernova can fizzle into silence, and that even the fabric of space-time can warp into funhouse mirrors around dancing stellar pairs. Every discovery peels back another layer, revealing just how little we truly comprehend about the forces shaping our cosmos. So where do we go from here? With next-generation telescopes like the Vera Rubin Observatory and the James Webb Space Telescope probing deeper into the infrared and gravitational wave detectors tuning into space's faintest ripples, the next decade promises even wilder revelations. Could we find binaries where both stars are cloaked in dark matter, systems where time flows differently for each partner, or perhaps evidence of stars orbiting primordial black holes from the dawn of time? The possibilities are as infinite as the universe itself. Now it's your turn. Which of these discoveries stunned you the most? Do you think we'll ever find a binary system that defies even our wildest theories? Drop your thoughts in the comments, because the beauty of space is that it's a conversation without end, a mystery that grows richer with every question we ask. And remember, the night sky isn't just a static canvas. It's a dynamic, ever-changing story, and binary stars are its most unpredictable narrators, so keep looking up. The next cosmic revelation might